Yeah, it's yeah, it's
So it's like, whatever.
yeah,
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 So it's like, whatever.
yeah.
So it's like, whatever.
Yeah.
So you are the trouble. See? It's making to this. So see, hello? No one is connected to the Zoom yet. But only if someone is connected and you see we can see. Hello, hello, hello. Yeah, hello. Yeah, good morning. Good morning.
Every good morning. It's lagging.
Yes,
This one they talk at the for wait for.
I was supposed to hear something. I think that was what was conflict. Like, mm, you don't really got it.
Hello. Hello.
That's fine.
Yes.
Trying to zoom, then share your slide. Use online.
Okay. So how do I connect? So I need some wireless, or how do I connect to
Internet.
Yeah.
D for DA.
Small d,
Yeah.
e for e, a,
36
b6.
44. Jabra. 36. So it's working, but it's also giving a feedback.
So I mean, I need to zoom. So where do I find it?
Yeah. Can we generate the zoom? You can use the ID.
The zoom.com or
Yeah, the union. There's no zoom installed on the
No
Zoom.
zoom
Online.
maybe the ID 5 is
H2
wait. 915
and H295.
H
H
2
95
95
8484.
84.
Outside. Outside. This is what we might do. Anyway, if you switch it off, how do they do it? So get I don't see understand we need data feedback. Now we have it up. Like feedback now kasa I over now. Seven 757
775
757
756
162.
162.
eight. The post is over, then we get it.
Let's wait and see. Right, feedback, yeah.
Who's have you tried? You tried. So it's time to pay now.
Wow.
Are you ready? Okay. So since I like the application, then I don't have any
Yeah, that.
so she just respond that.
Nice one, but yes.
Ready to the next break.
Check. But example, he can't hear you.
Okay, let me start.
Hey,
Hello, good morning, everyone. Want to enjoy today's class. I your time. Unfortunately, we want to. Hello, good morning, everyone. Everybody.
That's what we said. Bring it.
Okay, so as I said earlier, I hope you had a good sleep or good night. And we are gathering the channels to make that available to you. So as I said earlier, people can cross some information. And I believe that they started from the basics, from the configuration of interactions and all of that. We are pleased to have Daniel Ruben here. And yeah, combine or integrate the lower versions of the field with the higher version. So please spend be attentive to me and take notes. And then ask questions. Feel free to ask questions whenever you have to understand what about this. So
So check for my.
we are ready. We can start with Daniel Kuban for Daniel.
Thank you, Henry. Everyone, I'm happy to be here. And so my first advice is please use the occasion to ask questions. If not during the lecture, then during the break. I'm here the whole week and I'm happy to get into discussions with you. I'm going to have 4 lectures in total. So starting with the classical material simulation and then moving to the aspects of quantum computing for those material simulations. I started with the plan view of where I'm from. So, from an institute, which is part of the organization, which is one of the world's leading organizations for applied research. So, our mission is to bridge between university, between academia and industry. So this is quite a big organization in Germany. We have 75 institutes with different topics, different research proposals. Total there's 32,000 employees, so it's quite big. The business volume is several billion euros, and the point is that most of the money comes from projects, some either publicly funded research projects or projects directly with industry, and only a little amount of our budget is paid from the government. So we are always in the need of finding projects and offering something which is the Institute I found at the Fraunhofer Institute for Mechanics and Materials. It's situated in the southern part of Germany. You see some pictures of our institute buildings. There's actually in Karlsruhe, a town close by. We are roughly 300 employees there, with a budget of 23 euros per year, and 33% directly coming from industry. So also here, quite close to the demand of the industry. The institute itself. Right, here you have the zero that we're down here in France, between France, Switzerland, and Germany. So very nice part of Germany, the southern western corner. The institute itself has different research units, different business units, covering the whole aspects of the materials, so from material design, material manufacturing, some aspects of in life, so tribology is always a big topic, energy loss through friction. And there's many open questions here. Also new materials, lightweight construction is an important aspect. Then always lifetime concepts, lifetime prediction of materials. And so my group, materials modeling, is part of this assessment of materials and lifetime concepts business. Now, getting down to what I'm going to tell you in the next 4 lectures. So one is today, 2 of them tomorrow, and one in the afternoon, third one and the day after tomorrow. So today will be about atomistic modeling of well, first in general, and then especially on this electron correlation effects in materials. Why that? Because this aspect has a promise that quantum computing can help. So let's first look at what is done classically, where are the bottlenecks, to see whether and how quantum computing can help. Then tomorrow I'm going to introduce the framework of how quantum computing can come into the game. And this is called dynamic field theory. That's our approach. There are several other approaches around, but it's always a kind of embedding. I've seen some of you at coasters on Friday, where they also think about taking singling out some part of their problem, trying to solve it on a quantum computer. And there's always an embedding, that you have some theory which describes the system as a whole, and you have a more accurate method to calculate some specific part of that system. That's what you call an embedding. And so concepts that I'm going to show here, you can also translate to other theories, embedded theories. And then in the third and the fourth lecture, I'm directly showing you our work on quantum algorithms for this kind of models here. Of course, all the quantum algorithms are still in a proof of concept stage. As you know, since noisy quantum computers are still noisy, you cannot really go to real world problems, but you can already identify the bottlenecks and what is needed to, in the future, run successful quantum computing calculations. And the thing is that we had, for the last years, some substantial amount of access to IBM quantum hardware, so we could really test the performance of algorithms on the hardware. I'm going to show you the results of those lectures. So, in general, when preparing these lectures, I was a bit insecure because I don't really know what is your background, and I heard that it's quite a different background. Some of you are studying physics, some of you studying other topics. So I expect not everyone to be able to follow every aspect here, but I hope that I can give you the basic idea of the concepts, that you get an idea, okay, where do I have to pay attention when I want to tackle this problem? And then you can go into depth. And as I said, please ask questions also during the 24-hour lunch break. So, coming back to how I understand, and we at our institute understand materials and materials properties, we always try to go the whole way through the different scales, from the structure, down from the atoms to the devices and products. And so every material is in the end made of atoms with electrons. So there are the nuclei and there's electrons. So that's really the basic scale. Those atoms are assembled to a crystal structure, which is periodic in space. And you can look at these crystal structures, for example, with the density functional theory that some of you are also using. But then that's not the whole story. Then there comes a very important scale, which is called the microstructure. Very rarely you have some material which is made out of a single crystal. That can happen for some semiconducting devices. But normally you have a lot of different grains, of different crystal orientations, maybe different phases. There's boundaries between that. So there's a huge, complicated microstructure. And many material properties originate on this scale. Finally, what is happening here is determined by the physics of atoms and electrons. But it's very difficult to get this path and then finally make predictions on the behavior of a macroscopic product or macroscopic hard piece of material. So when we want to understand the materials and where the properties come from, and we need this understanding to modify properties and to fine-tune or optimize properties, many of today's materials should fulfill not only one functional requirement, but maybe many. There might be some lifetime requirements, there might be some functionality, piezoelectricity, some mechanical property, like durability, whatever. So there's always some multi-parameter space, some multi-functionality that we want to optimize. So going through the scales, there's a variety of experimental methods to characterize the material with macroscopic experiments. Like if you look for mechanical properties, you can really take a piece of material, you can pull, you can bend, you can whatever do with your sample. That's macroscopic measurements. Then there's microscopic measurements where you can really make very small samples, look in detail at what's happening on a very small scale, then of course there's all the electron microscope imaging that really gives you very detailed information on a atomic scale, and transition electron microscope images finally resolve positions of individual atoms. So you have the whole scale, different methods, and they are accompanied by the same scale of methods on the simulation side. So there's continuum models that work with differential equations. That's finite element simulation. If you want to simulate the response of some microscopic structure, you can build this finite element model with defining some grid on which you solve your differential equations. So these differential equations have many parameters that you either can take from experiment or you try to derive by the simulations. And then you can rely on microstructure models that describe the interaction between these grains and phases and grain boundaries and phase boundaries. And if you want to parameterize those models, you can go down one more scale and look at atomistic simulations and molecular dynamics. And those simulations, again, require the information of really the lowest scale, which is the electronic structure and quantum mechanics down. And now along this whole multi-scale chain, let's say, we have possibilities where quantum computing can come in. So I wonder whether I can put this away, that you see it. There. So let's say that on the macroscopic scale, we have the solution of differential equations, of large systems of partial differential equations. So there are people working on, what's happening? There are people working on solving differential equations with the quantum computer. That's a whole field of research, very interesting. And if you could speed up the solution of partial differential equations, that could have a benefit in everyone trying to find an element modeling or fluid dynamics modeling. Those are there are simulations that really take a lot of time, a lot of computational power. So there's an opportunity to come in for quantum computing. Quantum machine learning is another important topic. I think there's also some lectures addressing that during the week. Here, for the material simulation, I would say you can imagine on a microstructural model, there's a huge parameter space of what can happen, how these orientations of the crystals are aligned, which phases are involved. It's really complicated, and to learn on how this microstructure then finally gives you a one value for macroscopic scales, like the yield strength of material or a toughness, which is just one number, which originates in all the microscopic features of this microstructure. There you can maybe use machine learning, and then there's the opportunity to use quantum machine learning to add something on regular machine learning. But it's an open question whether this works and whether this can give you a benefit. But that would be a point of entry for quantum machine learning. Then there's all sorts of quantum enhancement and quantum acceleration ideas on different simulations. But the one I want to go now to is the atomistic materials modeling with quantum computers, since that's my field of expertise, going to quantum chemistry and quantum physics. Something's happening here in the background. So for those of you who are not familiar with atomistic simulations, just a few slides introducing what atomistic simulations are. The good idea, the good thing about atomistic simulations is that you have like a laboratory in your computer. You can build structures like building structures from Lego. But now in our case, the Lego blocks are the elements from the periodic table, and we can put them together to form nice structures, and we can do calculations on these structures and do a numerical experiment. So in our numerical experiments, we have direct control where each atom is, and therefore can look at what happens, for example, when we change atoms, when we change the structure, when we move atoms to the structure and all that. Now, here's again a picture of a microstructure. This case, it's a piezo response force microscopy image from lead zirconate titanate piezoelectric material. And you see the scale is 1 micrometer here. And you see all sorts of things happening here. We can have a look what we see here. So there's grain boundaries between crystalline grains. There's maybe you can see on that scale, maybe there's point effects. That means there's other atoms that can either be put there on purpose, then you call it doping, or they're not put on purpose, then it's degradation or dirt or whatever, impurities. But it's not necessarily only lead, zirconium, titanium, and oxygen in the material. There can be anything else. And so these are then what we call point effects. Then in this case, because it's a piezoelectric material, there's a piezoelectric polarization. And this polarization can be different in different regimes. That's what's imaged by this piezo response force microscope. So you have the polarization pointing in different directions, and that can also change into what is called domain walls. And then each of the smaller part, if you go down in scale, is some perfect structure. So from the atomistic point of view, what can we do? Well, we can look at maybe what are the properties of this perfect structure. So we zoom down and look what is the perfect structure, how does it look like, what is the basic properties. Then in the second step, we can maybe look at what happens here at a grain boundary, or this is shifted, should be the grain boundary. What is happening at the grain boundary? We can build a model for the grain boundary. Then we can look here, what is happening if I put a point effect? I can get an understanding, what is the chemistry when I replace single atoms in the crystal structure? And then maybe I can look at what is happening at the phase boundary when the polarization changes. So each time I just get a small piece of information on this huge microstructure. And then it is the challenge of putting those pieces of the puzzle together to get an understanding of this material and its behavior. And here, for example, this is the crystal structure at different temperatures. It's either cubic or tetragonal. When it's tetragonal, you get this polarization. So this is this lead zirconate titanium, and you can build complicated structures like here. That's dislocation course, and you can study what's happening here. But the point is, I always have just a small piece of reality that I can look. So if I zoom this piece up, so this is now the micrometer, then I can put the pixel here. That's 10 nanometers. Yeah, I don't know whether you can all see it. It's 10 nanometers, and 1/10 of that is 1 nanometer, which is about the scale you can do with atomistics. Yeah. So the atomistic scale is angstrom, and you can do 10 angstrom, maybe 20 angstrom, but then your system is getting too large for normal computational resources to be treatable. So that's the gap of the scales between what you can do atomistically and what you want to describe finally. Okay, so when we do these atomistic simulations, what do we need? Well, we need information about the structure. So that's essentially atom types and positions, like again, sketched here for some structure. We can put atoms that define position in space. Then typically we always consider periodic boundary conditions, so we do not look at a cluster of let's say 20 atoms here, but this resembles an infinite crystal because we always consider periodic boundary conditions in all three directions, but it's a perfect crystal. Then the second ingredient is the interaction between atoms and electrons, and here we start to make approximations. We have to find some model how we want to describe the interactions between atoms and electrons. And the third ingredient is, okay, once we do the calculation, whatever we want to do, how do we derive the properties that we're interested in? Mechanical, electric, optical, magnetic. So there must be coming some theories coming in here, how to derive physical properties from, let's say, positions of electrons and atoms. And there's two major approaches how to do that. That's either to use as ingredients between so for the interaction to use classical physics. So that's just taking Newton's mechanics, so having forces between atoms, or taking quantum mechanics, and that goes then to Schrödinger's wave mechanics, using wave functions, complex wave functions in a Hilbert space. And so the classical physics, to do that, you need to know how are forces between atoms. Yeah? And that's what's called interatomic potentials. And there's a whole literature about interatomic potentials. But you need to parameterize. Yeah, you need to fit to something to come up with some idea how atoms in a crystal structure interact with each other. Well, on the quantum mechanical side, it's parameter free. That's why you also always talk about ab initio. There's no parameters at this point. There will be approximations later on, but at this point, there's no parameter. Then the theory or the methods that follow from this idea is what's called molecular dynamics, or sometimes also molecular statics. And here, the work was density functional theory. Here you can treat many thousand atoms. You can do easily 1 million of atoms. Yeah, takes some time, but you can do it. Well, the density functional theory is restricted to a few hundred atoms. It depends on which type of atoms, because each atom has a different number of electrons. But you're really restricted. Computational time here grows at a power n squared times log n or something, and that blows you up. So the largest calculations me and my group ever did was 1,000 atoms for carbon. That worked because carbon is a small, slight element. And for metals, I would say 150 atoms. So not because we could not do larger, but we didn't want to wait that long. Yeah. And if you do a density functional theory calculation, single calculation of, let's say, 60 atoms, that can take you 1 hour. If you take 150 atoms, that you can take maybe a couple of hours. And if you do 1,000 atoms, metal atoms, that could take you days. So what is the outcome of molecular dynamic simulations? It's atom trajectories. There's no electrons in MD. There's just atoms or ions with interacting forces. So what you can do is look how do they move at finite temperature. And so if you can do time evolution, that's why it's called dynamics. So you can look at trajectories of atoms. On the contrary, in quantum mechanics, you can't do that. It's an electronic structure calculation. So the atom positions are fixed. You only get ground state information at 0 Kelvin, absolutely stationary. So why is that important at all? Because many of the properties of a material originate in the electronic structure and what the electrons do. So that's really important. So deriving material properties you can actually only do by density functional theory. And if you do it by MD, then it's because the MD is parameterized by density functional theory. So you can always do density functional theory calculations and parameterize some interatomic potential to do the job. But that only works if there's let's say, if there's a good argument why the details on the electronic structure do not matter. Yeah, like for example, for mechanical properties, elastic properties, you can always fine-tune these potentials to give you the correct elastic response of a material. When you fitted it to density functions, you can also fit to experiments. Yeah, because that's elastic response is an elongation of bonds. So you can put that in a potential. Yeah. While if you want to look at the properties of a semiconductor, and you need to look at the structure, you look at band gaps, at excitation, nothing of that is in the molecular dynamics. So you have to go back to DFT. So and also DFT will be what we'll be looking at. I see no possibility for quantum computing in the MD sector, but there will be for density functional theory. So let's go to this point. And here's a big formula. Don't be scared if you haven't seen it before. That is the equation we need to solve if we want to look at a system which has n electrons and m nuclei. So we need to solve this eigenvalue equation here, where there's some operator H, Hamilton called a Hamiltonian, acting on the wave function, which depends on all these coordinates of the n electrons and the m nuclei. And it should be an eigenvalue equation, so there's a constant, the energy, and the function. That's stationary Schrödinger equation. And so this operator here has many terms. So the first term here is describing the nuclear kinetic energy. Yeah? So the nuclei can move, and so that's the kinetic energy of the nuclei. The second term correspondingly is electronic kinetic energy. Yeah? The big indices, capital I, respond to the nuclei, the small indices to the electrons. So we have nuclear energy and electronic energy. Then we have the Coulomb repulsion between the nuclei. They are charged, they are positively charged, and having charge numbers capital Z and distance Ri. So that's Coulomb repulsion between the nuclei. The double sum. Each nuclei interacts with each other. Then we have the same term, Coulomb repulsion between the electrons. They're negatively charged. Also, they repel each other with this 1 over distance. And you have this double sum. And then finally, there's the attraction between electrons and nuclei. And these are the ingredients that build up all our structures. And it looks, on the one hand, simple because you have just these 5 terms. On the other hand, it's extremely complicated because you have all these different coordinates. They're all intermixed, and this problem is absolutely not solvable. You can solve it for 2 particles, and then you're done. So there's no parameters here, no empiric parameters, but it's not solvable. So we have to think about something. What can we do? And so the first idea coming into play say, well, the ions or the atoms, the nuclei are much heavier than the electrons. So in principle, they should move much slower than the electrons. So can we decouple electrons and nuclei? And that's what goes under the name of Born-Oppenheimer approximation. It relies on the fact that the mass of the nuclei is more than 1,800 times the mass of the electron. So it's reasonable to assume that the nuclear degrees of freedom can be factored out. We can just take them as fixed because the electrons respond so quickly to the nuclei that we can take a more easy problem here where we have an electronic Hamiltonian acting on now a wave function which only depends on the parameter on the coordinates of the electron, so from 1 to n, and all these capital R's, the positions of the nuclei, they are just fixed at a certain, and that's what we had in the DFT. We put the atoms somewhere, and then we calculate the electronic structure. So how does that reduce the complexity? Now we only are left with this kinetic term of the electrons, this one here, and the Coulomb repulsion between the electrons and the attraction between electrons and nuclei, and the ones of the nuclear kinetic energy, and this one have vanished, and they will just give you a constant in the end to your problem. So we reduce the complexity a lot, but still it's unsolvable because now we don't have n plus n degrees of freedom. We have capital N degrees of freedom. That's still a large number for a material, for a realistic system. So even this one is not solvable at this point. So before we continue, are there any questions to this? Is familiar to you or not? Yep. So that comes from you have the derivatives here, and that's from the formalism of quantum mechanics that the operator given the kinetic energy is minus then the second derivative. That comes just from the way of describing quantum mechanics. If you put a real wave function, the value will be positive. The question is about how do you derive this kind of exponential organisms. This is really a very difficult task. So first we must find some data from calibrate. Then usually when you do it specific, you'll see that in some of the elements compromises. We'll never be able to get perfect fit with the data, otherwise it's you will see equivalent. You lose a lot. Yeah, when you go from the DFT to the LD side. Let's quickly go back. So when you go from the quantum mechanics to the classical physics side, you lose a lot of it. So it's not, you can never get a perfect fit. You have to choose. For example, if you want to get a good fit to describe mechanical properties, then maybe something else is wrong. Yeah. So I've always then, so every fitted interatomic potential is able to describe what it's fitted for. Yeah, and it can never fit many properties at the same time. Yeah. So if you want to derive your motor, I would really be very careful in trying to derive your motor interatomic potential if you put this it's not something to do easily. So we usually, if we tackle a problem, we see whether there's literature around where someone spent his whole PhD covered with rising interatomic potential, then we can take it. Yeah, otherwise it's really a big effort. And one thing which is now on the market is machine learned interatomic potentials that come pre-trained, that are already trained to huge data space of DFT data, which are available freely online. And so you can, my experience is that if there's not a specialized interatomic potential published in literature that we can take, the next step would be try to use these machine learning interatomic potentials and to fine-tune them with your own data. If that does not work, then you have to do the hard job and parameterize. But it's not easy. So the question was to spend another few words on the equation. The point is, and then go back, why these equations look like this originates in this quantum mechanics, in this Schrödinger equation for quantum mechanics. And I cannot, in this short time, derive or explain why physics at the atomic scale is governed by this type of equation. Then you need a whole lecture of quantum mechanics that explains why electrons, which are quantum objects, behave with this kind of equilibrium. But just to get you an idea, this is the complex function side, and this complex function obeys this equation that the time derivative of this complex function is equal to some operator, so it's a differential operator acting on this function. And from that you can derive, if you do the approximation, that you want to be in the stationary case, so that helps you to solve this equation. Then this equation boils down to just an eigenvalue equation. And this is Schrödinger equation, a field stationary Schrödinger equation, where you have some differential operator which depends on all these terms. So there are derivatives here, that's second derivative with respect to the coordinates. So it's a differential operator, and there's some just multiplication terms, and this acts on this function, and this is a complex valued function. And if you haven't studied this, and it's hard to follow each detail, But the point I wanted to make is the meaning of these terms. The meaning of these terms you can understand easily because you have two types of species, which is nuclei and electrons. Both move in general, so both have a kinetic term. So these are the first two. And in the whole framework of quantum mechanics, the kinetic energy is calculated by a second derivative working on this function. And then you have three terms with the Coulomb energy. And Coulomb energy is always 1 over the distance and a charge of the one element times the charge of the other element. So all these three terms are in that way. So here it's a charge of the one nuclei with the other square divided by their distance, and here's the charge of an electron multiplied by a charge of an electron divided by the distance. And the factor of 1/2 is here because you have double sum and you avoid double counting. Yeah? Because you have one term where maybe I is 1 and j is 2, and you have the other way around. So you have twice in your sum, and you have therefore taken the factor of 1/2. And what I missed here, of course, I equals j is not allowed in the sum. Here you don't need the 1/2 because you have different objects, nuclei and electrons. So that's the meaning of these three terms. It's just Coulomb interactions and kinetic energy. So potential energy and kinetic. And here down here it's the same. Yeah, it's kinetic energy and potential energy. It's potential energy of the electrons between each other and the potential energy of the electrons in the field of the atoms. Yeah. The question is about the overcounting. So since I have a double sum, and each sum goes over all ions. First of all, you have to exclude that I equals j. I didn't put it here, sorry. But then you have maybe in the first sum, you maybe have j equals to 1, and in the second sum you have one term where I is equal to 2. So you have I 1 and 2. And then you have it the other way around. Also the sum j is at some point 1, 2, and I is 1. So if we have both terms, we have them twice in direction. Yeah, once with one of the guy being the first and the other the second, and the other way around. If you write down this double sum, you have each term twice. And that's why you just put it back. It's just summing up. You could also write the double sum that you have here from going from I equal to 1 to m, and here going from j equal I plus 1 to m, then you can avoid the 1/2 and just sum up the triangle. Okay, now the next step is, as I said, this is still too difficult to solve. This is impossible to solve, too many degrees of freedom, too complicated. And so here I just put it again. The problem is this is 3 to the 3 times n dimensional, and we have, even in the small supercells we're looking at, we have hundreds of atoms, so this is absolutely impossible to solve. So then, now we take a big step towards density functional theory, and that's the Hornberg-Kohn theory. So, Kohn, the whole density functional theory also goes under the name of Kohn-Shah density functional theory, and they received the Nobel Prize for the whole theory, one of the most employed theories nowadays. And the basic idea from Hornberg and Kohn was that, okay, this is much too complicated to look at the full function with all the coordinates. And so maybe we can come up with a description where we only consider the density. The density is just a function of one coordinate in space. That's the electronic density. So can we come up with a description? That's why finally it will be called density functional, because here is the density. Consider the electronic density instead of the whole wave function. And then they were able to derive mathematically, of course I can show you here, and but you can look it up in the papers. They showed mathematically that they can prove that there is a functional, and the functional is something that assigns one value to a function. So it's like a function of functions. That's the functional. So you plug in the function, which is the density in this functional, and you get out a value. And this value is always larger or equal to the ground state energy, regardless what you plug into this functional. And if you plug in by chance really the ground state electronic density, then you find the ground state energy. This is a very strong bound, let's say. So it tells you that once you know what is this electron functional, so what is this rule to come from a density to the energy, if you know this, then you can look at just what density gives you the minimum value of this function. So it's minimization, and you have done you got the solution. So it's called a variational principle. So you can play around with the electronic density and look what is the minimum to minimization, and then you're done. The problem of this theory is that it is a mathematical proof, but this functional is not known. Yeah. So it just tells you, okay, there is somewhere there's the holy grail, but we don't have it. It just tells you where to go. But this is the basis of density functional theory, because this is, as I said, it's functional and it put in the density, so that's why it's density functional. Okay, so with this alone, it's not very helpful. And as I told you, it's called Kohn-Sham. So there must be some guy named Sham. And so that's the second part to this, is a Kohn-Sham theory. And they say, okay, let's tackle this problem of having this functional that I don't know and putting in the density in order to find my solution, my ground state. And they say, okay, let's try to map the problem to a picture system of non-interacting electrons. Yeah, that will be described by orbitals. So it looks like atoms, but it's not. It's an auxiliary model. It's a constructed model of Kohn-Sham orbitals. And then we just make an approximation for this density functional. We say, okay, this density functional, again, will depend somehow. It will have some kinetic energy. And then there will be, again, some electronic Coulomb energy. And we take Hartree potential, we take the external potential from the atoms. And we just make this assumption that it looks like this. And then everything else, which actually is in this functional, which we don't know, I said it's not known, and the error we make by assuming it looks like this, we put into this, so this is everything else. So here we just have written a mathematical form for this functional, which somehow goes back to our intuition that we have kinetic energy, potential energy. So, and as long as, let's say, the problem we are looking at is actually really solved by non-interacting electrons, all this is fine. And if they are not non-interactive, okay, then there will be some difficulties, but this is all kept in this everything else, which for now I still don't know. So this is just a rewriting of the function. But if I do it like this, yeah, I can write down an effective potential by taking all these parts here, saying this is my potential of this Hartree term, the external potential by the atoms, and I take the functional derivative of this unknown guy, and this is my effective potential. And then I have a very effective equation here for my orbital, for my atomic orbital. And this is the single particle problem. And this is what is underneath the density functional theory. So if you're doing density functional theory calculations, you're solving this type. You're not solving this problem. You're solving this problem. Okay? And why is this not easy to solve? And you need all these codes and so on. It's because it has to be solved self-consistency, because in this effective potential here, you always have the density. Everywhere is the density. And the density is resulting from your solution. So what you do is you solve this problem with some trial density. You calculate the real density of your solution. You put the real density back into your problem, solve it again, get a new set of solutions for your orbitals, get a new calculation of your density, and do this iteratively. That's the self-consistency loop of density functional theory that you do when you run VASP or Quantum Espresso or any other density functional theory software. But it's a great reduction in complexity. Here, then we had a function of 3n dimensions, which are coupled through all these Coulomb terms. It's impossible to solve. And down here, we have a simple equation. Each equation just depends on the coordinates of one. So it's really single particle equation. You can solve that. The drawback is you have to solve it self-consistently, so you have to do these calculations many times, and then you can finally converge to your solution. So that made it possible to do calculations on the computer for electron structure of this equation, which at first sight looked impossible, and that's why these guys got a Nobel Prize at some point for that. That's why this method is the most widely used method to calculate electronic properties of materials, because it's computational, tractable, it's easy to use. You can, like Quantum Espresso is free to use open source software. You can directly download, you can download all the potentials, you can start your calculations today. And you get meaningful results. And that's the achievement of those guys, and then all the work following, putting that into usable software. Okay, any questions on this? The question why is it, so this is a functional derivative, yeah? Means that if I put this in a technical potential, it's like moving this guy anything. I want to describe everything in terms of potential. Yeah, and then I move, so because here it's just the effective potential, so I move this into here. Then finally, what is approximated will be this functional derivative. But since I don't know what this is, I don't know what this is, so I'm just this point, just writing it in different symbols, and I may have to make this is here. It must be approximated. I don't know it. I still don't know it. So I can make an approximation for this guy, or I can make an approximation. The basic idea, so to say, let's start to make an answers wave function that I can solve. The answers wave function is the product of one charm orbital. Looking at three orbitals, like three one interacting, but it's not. And the price you pay, the density of your solution comes in here. If that was not the case, then it's completely free particles. It would not see each other. Put it in here, I integrate over this, yeah, over the density. So that's just writing in the function form the functional derivative. It's not the real derivative. The derivative with respect to a function. Okay, so it's mathematically it's difficult. Yeah, if you do pure mathematics, you have to define how to do that with the integrals and so on. Yeah, for us now, we can think of, okay, if I put this guy into this integral, and I multiply by a rho and here I divide by rho somehow, it should work. Okay, but it's of course mathematically more difficult, but it's sound. And again, if you just look at this as just a notation at one point, I can make an approximation to this guy, or I can make an approximation to this guy, name it differently. Maybe gamma or whatever. So this is just from the notation to see where. But the important point is that you don't know it. Yeah? If you would know it, you have to bother. Yeah? If I know this one, okay, what is this? How do I do the derivative? But since I don't know, I just approximate this one. Yeah? final density. So this slide is again to give you an idea about this electronic correlation. So functional is called exchange correlation functional, and the correlations originate from Coulomb repulsion and from Pauli principle. And you can imagine the electrons in your material like a swarm of bees. Yeah? It's not that the motion is absolutely random, they avoid each other, they don't want to bump into each other. Yeah? So there is some average density. You can define some average density, but each individual, as soon as it sees the other bee, it will avoid each other. So the Coulomb repulsion and the Pauli principle, yeah, they result in the case that electrons tend to avoid each other because they're repelling each other. And so this will give rise to a negative contribution to the energy, which lowers the total energy because there will be less Coulomb repulsion if they avoid each other, if they try to be separated. And this whole thing also, if you come across in literature, sometimes there's a concept of the exchange correlation pole and density, meaning that the density, there's a spatial reflection of the electron density around the electron. No electron can be at the same spot of the electron. As soon as they approach each other, they avoid each other. So even in a uniform electron gas, there will be some uniform electron density on average, but the electrons avoid each other. They don't bump into each other. That's this correlation. Yes, each electron motion is correlated with the motion of all the others. It's not that the electron just moves in an average mean field potential, but it sees really the motion of the other. And that's, I think it's a nice picture with the swarm of bees that move around but always avoid each other. So having said that, another advertisement for atomistic simulations. I mean, all these developments have led to the current situations that atomistic simulations are really widely used, are crucial in today's material development and design. You can calculate a variety of material properties reliably, yeah, for a really plethora of compounds. You can consider what is your required accuracy you want to achieve. You can choose the method of choice to calculate this property. But the DFT really became the workhorse for atomistic simulations and developing material design and so on, especially for functional materials, for semiconductors, for piezoelectrics, for magnets, and so on. And the limitations of DFT, let's have a look at that. One has to be aware that it's, I mean, show you there's a, how you do it in general, but then you have to approximate this exchange correlation. We come to that in a second. And no matter what you do, there's always some drawback. So if you do it the basic versions of DFT, you will mostly get a band gap which is universally too small. And I will show you in the second part of the lecture today ways how to get around this, how to come to how to do DFT and get better band gaps. DFT has a problem with strongly correlated systems, has problems with van der Waals interactions. There's some static correlation error, and there's some shelf interaction. So all these limitations are known, and for all these limitations, there are methods to improve them. Okay? So it's just one has to then choose the method of choice depending on what you're looking at, and you can solve these limitations. A word to the self-interaction error. This goes in the direction of double counting that we had before. Microphones. Okay. So here's again the equation, the single particle equation we want to solve, where there's the Grondscharm orbitals, and now I've written out the effective potentials, and I said the potential, the Hartree potential, and the exchange potential, there will be the density. And I said the density is calculated from the solution. So somehow the solution of this equation enters in here. The electron in this formulation will interact with itself, because this function describes the probability of finding this electron at some spatial point. It contributes to the density, and it will interact with itself. And that's the self-interaction error that is inherent in a density description. Yeah, I mean, it is a sort of mean field, because this density is the average over all electrons. It's calculated self-consistency, but it's the average over electrons, so it's a sort of mean field which goes in here. And then you have this self-interaction of when you want to calculate, when you want to solve this problem of this function, seeing itself, that is one problem at the origin of why band gaps are wrong, and why there are some other of these errors. And where is this coming into play? Where is this going to be important? So it's not important if you want to describe aluminium, for example. It's probably also not important if you want to describe some other good methods, good metals, like gold. So for easy metals, this is not an issue. It becomes a big issue if you look at transition metals, and especially then transition metal oxides, which is one focus of our work. For example, down here, there's lanthanum iron oxide, a material used for electrodes in fuel cells. And the point for these transition metals, they have d orbitals, and the same is true for rare earth elements that have these f orbitals. So why are they special? Why are they coming? Why are they important to look at these errors? The point is that if you fill up the shells of the periodic element, going from left to right, here first you start filling up the fourth s shell, and then there's the 3d. And the 3d is more confined to the nucleus than the 4s shell, but the 3d also contributes to binding. And so, on the one hand, those electrons are very much localized, close to the nucleus. On the other hand, they are still spilling out to their neighbors and contributing to bonding. And that is here that you have an interplay of localized orbitals. And that is like a particle-like picture. They have a defined position in space, and the bonding and the movement, the itinerant behavior, wave-like picture. So for those orbitals, and these are the 3D, and also here the first row of S, the 4F orbitals, those are particularly interesting for these kind of corrections because they are so localized that this self-interaction and this seeing each other when moving is very important. If you have S orbitals, they are extended in space, the error you make by this self-interaction is not very relevant. Yeah, but for the D and the F shells, since they are localized in space, electrons see each other all the time, let's say, and it's important. And the thing is, why is it important that they still contribute to bonding? Well, if they would not contribute to bonding, we can completely forget about them, and they would be just sitting there at the core and would not influence our whole result. But since here's a mixture of being localized and contributing to bonding and contributing to the whole structure, it is important that we take this into account. And the bad thing, I say, is that transition metal oxides is a very important material class, and also rare earth containing materials is a very important material class. That's why it's important to look at these drawbacks of, let's say, vanilla flavor DST to come up with a better solution, because we want to have good description of transition metal oxides or rare earth containing compounds. So transition metal oxides, for example, in our case, it's electrode materials for batteries, for fuel cells, for catalysis, and the rare earth containing compounds are usually magnets. If you want to have high performance magnets for energy conversion, for electric motors, for electric generators, you need these materials that involve those elements. And then if you want to design them, you want to optimize them, you want to have a good theoretical description. So that's the point where we have to think about how to extend our theory. And so the question is, how can we fix those limitations of conductivity? And then there's a variety of methods around when you go from weak correlations to strong correlations. So, and again, this depends on which structure you're looking at, which compound you're looking at. And there's a variety of methods. I just want to name a few here. So for the van der Waals interaction, this is long-range correlations between dipoles. There are many empirical dispersion corrections available that you can easily use. Your PFT code, it's just one line. You can use those additional and try out those additional correction terms. There are some non-local exchange correlation functionals. There's a so-called self-interaction correction, which I'm going to talk to you about the second part. So it's self-interaction corrected. LDA, for example, there's another method very similar. It's called DFT plus 1/2. You can use on-site repulsion for selected orbitals to get rid of this too strong localization by introducing some Hubbard U term. There are these hybrid functionals where you have mixture of some Hartree-Fock exchange. So they have a variety of names. There's many around, and so on. So there's a whole bunch of methods that people have developed to cope with those limitations. And if you look at a material where you expect these correlation effects to be important, you can go to the literature, you can look at these methods and choose the one of choice to give you correct predictions. And it's this ongoing research, which method is working best for which material. And always it's also a question of computational resources. Different methods come with different computational costs and accuracy. And if you're down to the strong correlations, so really this perovskite type metal oxide compounds for high temperature superconductors, or for these electrons or fuel cells or electrolyzers, what I mentioned, intermetallic rare earth transition metal compounds, for high performance permanent magnets, then you might want to go beyond this and use this DFT plus DMFT framework that I'm then tomorrow, and where then the quantum computing can come in. So but this is, let's say, the toolbox we have without any quantum computing, without any limitations. Just, I mean, for the hybrids, for example, it's computational resources, or the non-local, they are computationally more demanding even than the standard DFT. But if we have enough computational power, we can choose the method we want. And only it's down here in that limit, even those methods then at some point fail, and we have to do this other theory. Okay, so I'm here, I think it's a good point for making a break. The second part will be showing a bit how we use this method to describing really some materials, calculations for transparent conducting oxides, which are also, in this case, that's the transition methods of oxides. So it falls into that class. It's not this strongly, there's some medium correlations there, but you will see that you definitely need corrections. And I want to highlight these two because they are, for this class of materials, very efficient. They don't increase the computational cost, and they increase your predictability of your results a lot. Yeah, that's a question. And avoid by are not prepared with so which doesn't way topics, so we had time to say the bottom. That's the best way to do. Okay, that's an idea. Make that. It's a more. Research. And I could decide you were not much. I was nothing.
I'm not sure.
Everything is different. Everything is centered around. But people that able to go to meet them, there is no thing for them that they can like let's see how this. What's happening? This is not because it's all they don't always. Oh, for example, let's see that this was such a You don't need to do this. The same, I think, it's long, as you propagate the wrong result. Okay. More accurate measure. How much time? Okay, I mean, it can do. All right, welcome back. The second part. I said the second part will be now on a specific material, just giving you the example of some calculations we did. And that is especially my colleague Wolfgang Körner and I did that, the supervision of Christian Anderson at that time. And it's about band structure and subgap state in amorphous transparent semiconductor oxide. So probably none of you have worked with these transparent conducting oxides, so, but this does not matter. It's just to illustrate what is possible and to produce also some ideas, because some of what we did here, at least I have the impression, connects to what I've seen on some of your posters. So the general background about these, that is, I call TCOs, for transparent conducting oxides materials. You all have them on your mobile phone, for example. They should be transparent, so they can be used for screens or solar cells, and at the same time they should conduct electrons. And this is some two actually contradicting properties, because transparency means a wide band gap that no light is absorbed. On the other hand, electron transport means that if you have a semiconductor, you need to have states close to the band gap, so you must find a compromise in having electron conduction and transparency. So, and here, the point was this: these materials are in general, again, oxides, it's the O, and the most widely used material, probably on those screens and on your mobile phones, is indium, gallium, zinc oxide. Indium is a scarce element, pretty expensive. So the question at that time was, are there alternatives? And for example, zinc tin oxide, which is cheap elements, green, non-toxic, and we don't need indium. And we want to look at amorphous structures because it's more easy to process than if you want to have single crystal. But to understand whether this material can be used as a transparent conducting oxide, we would like to predict what is the influence of defects and doping. I said we need to dope this material to have electrons available for electron conduction. So we cannot only use zinc, tin, and oxygen. We need to put some other stuff in there. And so how does that affect the band gap? And so in general, the question will always be, what is the band structure and the band gap? And here's a sketch. You typically look at the density of states as a function of energy. So you plot which electron states are available, and you will in general find that there are some peak here, which is called the valence band. So these are all these orbitals that contribute to the binding of the material. And then you have the unoccupied anti-binding orbitals that form the conduction band, and they're generally empty. And then you will have defects, and those defects will make some mess here in between. So in general, for good transparency, you would like a band gap between the valence band and the conduction band, so that the light goes through, it's not absorbed. And for the electron conduction, you need some doping, which gives you some electron states here close to the conduction band, so that electrons can move through the material and carry the current. So as said, the deficiency of standard local, semi-local LDR or TTA exchange correlation functional, so that's the standard DFT, is that the bandgap of semiconductor is small, typically underestimated by 50%, and we get a bad description of these localized D bands. Whereas D band here, zinc was in this element, in this material, or if we compare to indium, those are elements that have d orbitals, and they exactly fall in the class of these materials where we have this self-interaction problem of the localized D bands. So the solution we took here was not to go to some computationally more demanding framework, but we wanted to implement the correction of the self-energy error that I tried to highlight on 10 minutes ago, and to correct this already on the potential level of the DFT code. And the idea is that you have your DFT terms here, and then you simply subtract again the Hartree term and the exchange correlation term from the specific density. Of course, that's still not exact, but it avoids this self-interaction with the total density. You simply subtract those terms with the density of this specific orbital. And you can do this on the pseudo-potential level, so you do this correction for the isolated atoms, assuming some occupancy, and then every one of you running VASP or quantum espresso DFT calculations, you always have to have a set of pseudo-potentials, so you can modify those pseudo-potentials to incorporate this SIC correction. And then the good thing is there's no increase in computational cost. Calculation just takes the same amount of time, you just use a different pseudo-potential for your DFT. And this works extremely well, as can see here. That's the band structure. It's an example of a more simpler material of zinc oxide in a Woods-Seed structure. If you do this classical DFT LDA calculation, that's the band structure. So you see there are some, I took it in different colors. Here's again the energy scale. Here's the band gap between the lower bands, which are occupied, the valence band, and up here's the conduction band. There's a band gap, which is here in the LDA 1.1, EV, which is much, much smaller than the experimental value of 3.4. You can identify here the oxygen states. If you look at the projection to atomic orbitals, you will see this is oxygen states here in that energy range, so from the 2p orbitals, and there will be the Zn3d orbitals down here, and they're far too close. So also from experimental, it's known that Zn3d states are much lower in energy. And so this is a consequence of this self-interaction error. And up here are the Zn4s orbitals, which are empty. And then if we do this self-interaction corrected LDA, so again, we choose a correction scheme, so we correct the self-interaction of the 3D to 100%, of the oxygen 2s 100%, and the oxygen 2p 80%. Then we arrive at this band structure here. And so it incorporates a more charge transfer, improved band gap, and an improved separation. So the band gap we get now here is 3.4, so it's exactly the experimental one. And more than that, in the same run, we have put the average D-band energy, so that Zn bands close to this experimental value, and also the bandwidth of the O2P is very close to the experimental bandwidth. So this very simple correction to the pseudopotentials gives you an accurate description of the band structure of zinc oxide. And again, there's no increase in computation cost. And so we were very happy about this easy method. If you would like to use it, it's not so easy because you have to modify your pseudopotentials, and modifying vast or quantum espresso pseudopotentials is not the most easiest thing, but I mentioned that there's this DFT 1/2 approach, which is very similar to what we did here, and it's readily available, I think, only for VASP. But some of you said they are able to use VASP, and now again this stopped. No, auch nicht. This one stopped. Those of you interested should try to get the information of this DFT 1/2 for VASP, and you can try a similar approach also there. Just the pseudopotentials are modified, and you can run calculations at the same computational cost. There's one parameter you have to fit, and this is this amount of self-interaction, this global amount of percentage of self-interaction correction. This is 80% here. This you have to fit, but there's only one parameter, and then with one parameter fit, you get the band gap, the band separation, and the bandwidth in good agreement with the experiment. Okay, there's a very prominent alternative. Yep.
The discussion version, the alpha.
Yeah. Yeah. No, it's not self-consistent. This is a tuning parameter. Yeah. So, yeah. So, and then this alpha also depends on the structure. So, for example, tin oxide, there's two different crystal structures. And so for one, it's set to 0.8, for the other, it's set to 0.7. There's always some sitting parameter in each of these zeros. The point here is only one. And the argument why we think we got the physics right, that we have one parameter and we fit three observables at the same time. I mean, if you want to fit three observables and your three parameters, most likely right. Okay, I want to use some words about a very prominent approach to cure self-interaction correction, and that is hybrid functionals. And hybrid functionals are also very easy to use because it's just one line in your input file. But my experience is also a bit dangerous, so I just want to tell you a bit more what is the problem with hybrid functionals. So there's what is called hybrid Hartree-Fock exchange. It's complicated here. Hartree-Fock exchange involves what is the consequence of exchanging electrons. So it has the wave function, the red wave function, and the blue wave function in the integrals. And you have the coordinates exchange. So you have the red one with the coordinate r, you have the red one with the coordinate r prime, the other way around. So that is exchanges, let's say some exchange of particles in this kind of Coulomb term. It's a purely quantum mechanical terms. No classical corresponding thing. It's a quantum mechanical feature, and this is the way you would calculate it if you would have a set of wave functions. So Hartree-Fock is a wave function approach. So this is not a DFT. DFT is a density approach. This is a wave function. But once you have your Bourne-Charme orbitals, you could put them in this probabilistic graph and kind of calculate this value. Okay, and you know that this is an exact exchange term for so these hybrid functionals now come to play with this quantity, and they say, oh, okay, our exchange correlation, now we take 25% of this guy, and then only 75% of the classical TTA TE term. for example, or someone else comes with what's called HSE, says, okay, we take 25% of this on a short range, and on the long range, we take it equally. So there's all kind of fiddling around on how to put information of this guy into functions. There's an EV3 lib with all these numbers which instead of calculation. Okay, now what to use? You can use this one, you can use this one, you can use this one. You have to, in the end, try which is giving you a good description. The point is that all these have some empirical fittings, some empirical parameters, and the danger is that you get the right result for the wrong reason. They are not, these numbers are not reducible. Right. I mean, the same thing, of course. As I said there, since we have one parameter which fits three observables, we have some confidence that we're getting the right physics. Yet, just to point out this danger, if you have a method which gives you the right result, does not mean it's right. You can give it because it's fitted to give that result. It doesn't capture the correct physics. And as soon as you leave the area where it was fitted to, you might get predictions which are wrong. So, and the point is, it's not so easy to check how these work, because this is really computationally demanding. You have a double integral. It screws up your computational time of the DFT calculation. It takes much longer. So you then start to play around with the convergence parameters, you relax the convergence parameters, and then you're in the danger of having a wrong description from the start. So it's very, it's demanding to get meaningful results. Nevertheless, it's widely used because where the file you have it, you need to understand it. But be careful, can easily produce long-running calculations. So we checked it, for example, or we checked it, some other group checked now that the predictions of these hybrid functions for the band structures. And you see the variety of band energies of this D band and the band gap. So it's absolutely not clear. You need to run them in the different versions, find out which one is the good one. And then the best one is where they played around with the parameter going back. So they tuned this 25%, they tuned it to be 37.5, and then they got quite a good agreement. Okay, so it's just a word of caution for hybrid. We then went on and looked at the amorphous structures, and I also wanted to show this. How to model these disordered amorphous structures, because I was seeing people with posters on disordered larger structures, and some of the concepts might be transferable. For if you want to look at amorphous structures, it means it has not a crystal structure. It has a disordered structure. So how do we come up with a model for a disordered structure? First place. So this is a crystalline version of indium gallium zinc oxide. There's a nice layered structure, and now we want to come up with a disordered version of that. So what we can do, we can run MD calculation with some basic interatomic potentials. We cook this up, we cool it down again, and then of course it will end up with some disordered structure. The disordered structure we then plug into the DFT calculation and do a relaxation. Okay, we have a structure model. But again, if we do this the second time, we get a different structure model. So we have to repeat this many times, and then we have to choose which is a good structure model. I mean, I have no information from experiments that tells me something like this. So I always have to guess whether it's a good structure or not. And the thing what one can compare, maybe, if it's available, is what is called a radial distribution function. So it's the average distance between atoms. Sometimes this is available from experiments, sometimes not. So how does that look like? Here, for example, is a radial distribution function for the different atomic distances extracted from this structure. So up here it's for indium oxygen, gallium oxygen, zinc oxygen, and oxygen oxygen. You always find that it's a major peak, which is like this local order. This local order is not random because atoms like to be at a certain distance to each other, so that you see in these very sharp first peaks. And then you get a broad second and third peak, which is the vanishing long-range order. And so you're happy if you would have such curves available from experiment, and if you would the procedure to describe experimentally synthesized material. If not, what I did here, I plotted in the background the distances, the radial distribution function from this crystalline to see how does that match. And okay, you see you nicely keep the first next neighbor positions. They are well described, so it makes sense. But nevertheless, one has to check. One also has to check the average coordination numbers, and then in best case you say, okay, this is a suitable model for the amorphous material. But then again, we have to repeat this many times because every time we do this, there will be a different structure. And okay, this will be 100, 150 atoms maybe. But the structures look different. You can also already see from the eye that they look different. And so you have to do multiple calculations. But you can get meaningful results out of it, given that this structure is large enough. And to know whether it's large enough, let's recall that we look at periodic boundary conditions. So this structure that we have here actually is continued in all three dimensions. So we continue it in X, we continue it in Y, and we continue it in Z. So effectively, we model this type of a structure. So on long range is again a crystal. So in order to assure that we make no error in doing this, we have to see that this unit cell is large enough so that we don't have finite size effects. So this is the compromise of this unit cell to not have finite size effects. And what I mean by finite size effects is that if I have some impurity, some defect I want to look at, there should be no interaction between this defect and its image. If the structure is large enough, then it's okay because this one does not see this one. But this becomes a problem if you look at charge defects. The local charge defects, the interaction range is pretty long, you have to do correction and so on, you have to be careful. But if you are sure that the dimensions of your cell are sufficiently large, then you have a good description of an amorphous material. And this again goes in the direction of what you can do with hybrid functionals. If I have a very computationally demanding method, I need a small cell. Then I have a sophisticated method, but the cell is too small because I have error of finite size. And then again, I have to find a compromise. And that's why for these materials, for the amorphous materials, so zinc oxide I showed before was crystalline, it was very small cell. Yeah? I would really not like to do hybrid functional calculations on the amorphous structures. We did a few, and it was really very time consuming. Yeah, please.
Slide, put slide. The last slide. Yeah. Average practice. Each of the yes. Let's see, but we need to compute the minimum relation. That's what it is. Unless you want to really manage, but if there's not, that's something. How do you get
How do they RDF extract the radial distribution function? How do they relate the energy? So my first argument would be that I say I repeat this many times, but I study all or a subset of structures. I do not select structures with integrated. Because on this side, the very small snapshot, it's not meaningful that this one structure is 0 point something EVs lower than the others. Yeah, so that, because that would mean, okay, you do this many times and then look at one structure. That is too narrow. Yeah, so if you take, we usually took 10 structures, 10 different structures with some distribution of, and the RDFs are not that different. Yeah? They're not that different. If they would be very different, then I need to worry that my system is just, because then I might log something because of this bias. Yeah. So that's what I mean. We need to check also that if I repeat it, the average does not change so much. The local configuration changes and the local energies they vary for sure. And especially if you have feedback, looking for not only look at the minimum energy structure, but take a sufficient set that shows you what are different possibilities to occur. So it is a sort of statistics at the top. Other direct question here. One point I want to point out is that apart from this, so for charge, so in this sense, we prefer having larger subset of sharp ones. And then for disordered systems, we have also with crystalline disordered systems, sometimes you find people that take large supercells but try to look at one. And there I would say it's not the right way to talk. Then to look at variety of cells, because you must have a good argument why to single out one disordered structure. The disordered feature is important.
Because of process.
Yeah, because if you take a very expensive numerical method and you want to have a big cell, you can do it. But there I would say before waiting long time on this calculation of the one. And what I want to mention for material research, these amorphous or disordered structures are much more interesting and much more relevant than all the crystalline stuff. Because typically, if you, for example, any type of coating is always amorphous. You must be very careful in your experiment to really grow crystalline perfect structures. So most of the questions we are addressing from industry is, okay, I have no idea about my structures. When I put X-ray, I don't see it. So it's amorphous. So it's disorder. And also other, even there are also like alloys, so there's disordered crystal. And so this question of how to model disordered systems, that's really something with this ongoing research where you can make some progress. Modeling crystalline structures, that's crystalline structures you can download at Materials Project. Everything's there. There you can go into the direction of crystal defects, strain boundaries, excitations, all this. But pure bulk crystals, that is not. But amorphous structures, disordered structures, that's highly relevant because it's so difficult to model them. You get a good model, you get a good structure description, and there's a lot of interplay between the aspects of disorder and the elements and so on. Okay, how are we doing in time? Oh, so just one slide on what we get here. So this is the energy density of state, energy resolved density of state for this amorphous zinc tin oxide. Here, first of all, the crystalline version to see as a reference. The crystalline version, we have the O2P, again, the valence band. Whoops, down here, the conduction band up here is not just stars there, and the zinc 3D band separated by our SiC LDA. And if we now put the amorphous structure, what you see, well, you see a smearing of all those peaks because of the disorder. So the peaks broaden. It's not just this unique, but this averaged, this disordered bonding to the neighbors that broadens all the peaks. You get a broadening of the valence band edge, and you get some states, some defects, which are moving here inside the band gap. So these are exactly, let's say, the bad guys we want to detect. Why are they occurring? Which structural features give rise to these defects close to the band edge, which reduce transparency and which lead trapping electrons in the conduction? Now let's make the comparison and put the HSE result. So HSE, again, is one of these hybrid functionals. You see HSE gets the splitting completely wrong, although it is taking so much more computational effort, but you've seen this in the comparison before. It gets the splitting wrong. Therefore, all this is, there's also an error here in this state. It's not as deep in the band gap. So maybe you would, if you use just HSE, you would conclude, well, it's not that bad. And then you can compare B3 lib, yet another hybrid functional. You see the same kind of problem. Also here, the 3D separation is not well incorporated and the levels are too close. So our conclusions would here be that our description predict higher occupied levels, which are deeper in the band gap than the hybrids. The position of the 3D bands differs. And so this discrepancy between the different modeling comes from this different overlap of this 3D and O2 P bands. So the message again here is be careful in the method you use. Try different methods. They will probably give you different results. And then you can learn from that to choose the best method of choice. And just another example here, again, a different composition, same kind of features. We see that the SIG, our calculation, predicts levels which are far more in the band gap, so they're much more problematic, let's say, than what is predicted by HSE. And we were wondering, how do these two methods compare? And so if we remove, or if we reduce, we had this parameter alpha, which was 80%, we will remove ourselves, or reduce our self-indicted correction to 25%, and this was what was the parameter in HSE, was 25% after 4. We see that our curves on the defects align pretty well. We also see that we completely destroy this 3D O2P band separation, but we get the same prediction for the level. And on the other hand, if we so we can recover HSE when we reduce the self-interaction artificially to 25%. And on the other way, if we increase the factor in HSE to this 37, we see it's moving in the right direction, but still, if you look at the full picture, you see still the splitting is not correct. So the hybrid functional results are pretty wrong here. And that's our argument that for those materials, hybrid functionals just give you the wrong result. Okay, so this brings me to an end. That's our unified picture that we find here. We could identify in the band structure that the valence band is amorphous structures. It's broadened. There's some tail. You get defect states due to under-coordinating oxygen. You can get defect states to local metal defects. It's like a vacancy. I mean, in an amorphous structure, you cannot define a vacancy because there's no empty crystalline position, but you can look at local oxygen distribution, and so local oxygen deficiency is what you would call a vacancy in a crystal. So you can identify where these defects come from. You can think of possibilities how to cure that in your material, like temperature treatment or treatment by hydrogen. And we did this work for a whole lot of structures. So indium tin oxide, indium gallium zinc oxide, indium zinc oxide, zinc tin oxide, crystalline versions of that, zinc magnesium oxide, and so on. It's a unified picture. You can observe this physics in all of these materials. It has been shown by experiment that our interpretation can be backed up by experiments on this indium gallium zinc oxide. And so this is my advertisement slide for the clever use of these correction methods. And I said DFT plus 1/2 is another method which is easy to use and which gives you good results at a reasonable computational cost with a well-defined approximation, which to my understanding is not widely enough recognized. And I encourage you, if you look at those materials, take a look at those methods. That's it for today. But thank you for your attention and interest, and I'm around. That's all. We have some questions already for break. So, structures, the certain correction that we were using here is our own here. The second, how to modify it. So if you want to do something similar, this is method other people fast. So you can upload the fast to potential upload and modify this. In both cases, there's one parameter here. Because the correction will not depend on it. This correction will do both cases on the item. But on the description of the item. And it will depend where it's cut. So the point is that if you are doing different usage, different amounts of different environment. So finally, the organisms will have different localization, and so the amount of cell information is different, so they are not even correct. And there has been ideas of trying to do this consistently, but not really working. But it's always that one fitting parameter that you look at your structure. Of course, there are more to an average population. That's not the case, and so here and tomorrow, so even more sophisticated electronic structure approach, which is the DMFT, and that is then the entry point for quantum computing.
Hello guys. Hello guys. Please, the next class is going to start at 11, so you can stretch. Okay. The next class is starting at 11.
Okay.
Just an example.
So I would say this, but accurate derivation of and for something about possible services. About something that hasn't not with energy as it's been like with option. Person low energy was block. Don't go and eat today energy. Okay, that doesn't work. So those besides one there's still one structure. That the value of the exactly within bound of what I in the end, we don't know. What's that? Roll, they do fast. But it always take it. Oh, Let's look at states otherwise the error in that get enabled for that. But for five, what percentage change? What is the
There has been a little delay. The lecture is now coming. So please wait for like 10 minutes. Okay.
11, right? In the rapidly.
Okay, so how much time do I have?
So you don't have to watch so that you go from that.
But you,
So I'm calling the IT so that you go.
Good morning. Yes, so you right?
no, I'm not ready to.
You right.
Present slides.
You present right. So you can join Zoom.
Okay. Can I use the pointer?
Yeah, you get your printer. Produce the meeting info, meeting ID, then passcode.
And Wi-Fi?
The Wi-Fi you use not last.
Yes.
The password is D4 no, small D4 DA 3644. Yeah,
Oh, done.
yeah.
I didn't know.
Also, just coming to business. Get you the pointer.
Yeah. Seven. To turn on audio or turn off it?
John, yeah. You can share your.
People here today.
And basic. Great.
Good morning, everyone. So today I will be not concentrating on the derivations and the mathematics a lot, and I will just present an overview of the Hartree-Fock theory and what its limitations are, and summarizing the Hartree-Fock theory, and also how can we improve on the energy that we obtain from the Hartree-Fock. So to summarize what we were discussing yesterday, so what the Hartree-Fock theory does is it wants to solve for a multi-electronic system, a molecular system. It solves the multi-electronic Schrodinger equation, which is given, this is the Hamiltonian, the electronic Hamiltonian. It depends on two coordinates. Small r is the distance of the nucleus with the electrons, and the capital R is the distance between two nucleus in a molecule. This is the wave. Sorry. No. This is the multi-electron wave function that we solve for, and this is the final electronic energy that we get by solving the Schrodinger equation. So, using Hartree-Fock theory to solve for the multi-electronic Schrodinger equation, we get both the wave function and the energy as our results. And from the energy, we can calculate several properties of a molecule, like equilibrium geometries. We can calculate the Hartree-Fock energy for a whole reaction pathway of each molecule of reaction, and we can kind of try to predict reaction pathways using Hartree-Fock theory. And what the Hartree-Fock theory does is, as I introduced yesterday, it uses a determinantal structure for the wave function, and the determinant can be, in a shorthand notation, it can be written like a bracket. In the bracket physicists notation, we can use it like this. So this essentially means it's a determinantal structure, with the rows corresponding to the orbitals and the columns corresponding to the electron number. So what Hartree-Fock theory uses is this determinant as the approximate wave function, and plugs it in the Schrodinger equation and solves for both the wave function and the energy. So what the Hamiltonian looks like? As I mentioned yesterday, the one electron term of the Hamiltonian, it has a kinetic energy term, attraction between the nucleus and the electrons, and a two electron term, which is the repulsion between two electrons. And as I mentioned yesterday, from quantum mechanics, we can solve exactly a one electron Hamiltonian, but since we have a two electron term in the multi-electronic Hamiltonian, it cannot be solved exactly, and so we need the approximations. So looking at the structure of the Hartree-Fock energy, after we take the expectation value of the Slater determinant with the Hamiltonian, this is the structure. So the first term is the one electron Hamiltonian term. It acts between the orbitals, and then we get the Coulomb repulsion and the exchange repulsion. This exchange repulsion is the effect of the inclusion of the antisymmetry in the Slater determinant. That is, it enforces Pauli exclusion principle. It ensures that two electrons don't occupy the same orbital at the same time. And these can be expressed in terms of integrals. The one electron Hamiltonian expectation value can be written as in this form, and the two electrons can be written in this form. To explain what it actually means, so the physical meaning of the terms of the one electron Hamiltonian integral is, it's like an expectation value of the one electron Hamiltonian for an electron present in a specific orbital. And so we sum over all the orbitals to get the total electron kinetic energy and attraction to the nucleus. So if you remember, we have in the expression, we have a sum over I. So the Hartree-Fock energy the one electron contribution to the Hartree-Fock energy has the total electron kinetic energy as well as the total attraction of all electrons with a nucleus. For the two-body term, the first term, which is the Coulomb repulsion term, it's if you look at the structure of the integral carefully, you can see that on either side of the operator of the two-body operator, this part is the is a complex conjugate of orbital of one electron 1 in orbital I and the same electron in orbital I. So it's like a probability of finding electron 1 in the orbital I. Similarly, on the right hand side, it's the probability of finding electron 2 in the orbital J. So it looks like a very classical Newtonian kind of Coulombian thing, where we have the probability squared over the 1 by r operator. While the second term, which looks like it's not, if you compare these two, we have the same orbital I and I on the left side, J and J on the right side. While in the exchange, you can see that we have a mixture of indices of orbitals. So Ij, Ji. This does not have an equivalent in classical mechanics. This is totally due to the quantum nature of a fermionic wave function. As we had imposed antisymmetry in the wave function so that we can maintain the spin half nature of the fermionic wave function. This exchange integral is kind of a testimony to that fact that this is the quantum mechanics that we're using. So it has no direct physical meaning that has equivalence to classical mechanics. So this is totally a quantum phenomenon. So now coming back to the expression of the energy. Another property that we can keep in mind for the Hartree-Fock energy, the first two terms, that is the one electron and the Coulomb repulsion, these integrals will only survive. Since we have same indices on both sides of the operators, this will always survive in all conditions. So the electron can be either upspin or downspin in each orbital, and we will always find a non-zero value. But the exchange one, since there's an interchange of orbital indices, this integral will only survive if the electrons have the same spin. Because by Pauli's exclusion principle, if it's the opposite spin and it tries to occupy the same, this integral goes to zero. So if I give an example for a lithium atom, in lithium atom there are 3 electrons. So the first 2 electrons will be of opposite spin in the same spatial orbital 1, and the last electron, which is the unpaired electron, will be in a higher orbital, say orbital 2. So according to this equation, what will the Hartree-Fock energy be? We concentrate on only a restricted calculation set. So there are There are 2 electrons in orbital 1, so we'll have 2H11. There is 1 electron in orbital 2, H22. For the Coulomb repulsion, we have J11, so this is the Coulomb repulsion between this opposite spin electrons in the same orbital. Plus, you can see that this electron has a repulsion from both these 2 electrons. So we have a 2 factor here. And so the integral becomes 2J to 1. And as I said, since the exchange term only exists for if the electrons have the same spin in the orbital, so it will have only one exchange term. So here we can take So the exchange term will only be valid non-zero value for these 2. So these two have the same spin, alpha and alpha. And it will be, so this is the expression of, example of an expression of the Hartree-Fock energy for a 3-electron system. So now that we have an expression, how do we solve, how do you get the exact value of the Hartree-Fock energy? So these are just in terms of integrals. So to solve for the Hartree-Fock equations, what we need to do is we need to define a new operator, which I ended yesterday's lecture in this at this juncture. I defined an operator called Fock. The Fock operator is basically the 1-electron Hamiltonian operator plus a sum over all other electrons or all other orbitals, j minus k. So we have reduced this double sum over ij, and we have defined a new operator. So this operator is for each electron, we have a separate Fock operator. For each orbital, we have a separate Fock operator. And this kind of modification, this reduces the equation to a simple eigenvalue structure. So now we have a Fock operator acting on each orbital, and we get the orbital energy of each orbital as a consequence of solving this equation. But this is still a complicated integral because you can see we have a differential operator in the Hamiltonian, because the Hamiltonian 1-electron Hamiltonian structure is, it has a differential operator. Also, the expectation value necessitates that we have an integration. So this is a complicated integral differential equation. So it has both integration and differentiation within it. So to solve it, what was done was Clemens Ruthan had suggested that we simplify the equation further into a simple linear algebra problem by defining an orthogonal basis by which the 1-electron product, 1-electron orbitals can be defined. So say we have a orthogonal basis, any arbitrary orthogonal basis called chi tilde, and we express each 1-electron wave function as a superposition or linear combination of the orthogonal basis. If we use this, the equation simplifies to values whose values we already know, because we can calculate the overlap integral between the two bases. We can calculate the Fock matrix. So it gets a very simple matrix form instead of a complex integral differential equation that we have to solve every time. So this is more analytically easier to solve. We can just diagonalize the F matrix. We know the C coefficients because we know the relation between the two bases. We know the overlap, and we can easily find the Hartree-Fock energy. So the procedure by which we solve for the Hartree-Fock is we first select the molecule. We choose the appropriate orthogonal basis function. Then we want to choose what state we want to solve for the molecule, say the ground state of singlet, multiplicity, or triplet. We form the overlap matrix of S of the basis functions. We start with some guess coefficient C. So these coefficients C, we start with a guess. We form the Fock matrix. The Fock matrix is of the form this one. So it's just an expectation value of the Fock operator that we had defined. The Fock operator that we had defined. We get the Fock matrix. Then we solve for this equation, Fc equal to Sc. We get new coefficients for the next iteration. We again form the Fock matrix with the new coefficients. We do this until we see that the C no longer changes. The coefficients converge after under some threshold. And when it converges, we get our Hartree-Fock energy. So what we get after solving the Ruth-Hahn equation, Ruth-Hahn way of solving the Hartree-Fock equation is the electronic energy. We get the wave function, because every time we get a converged C, from the converged C, we can, since we know the basis function already, from the converged C, we can get the wave function chi. So we know the wave function now. We have the energy after convergence, and from the wave function, we can get a visualization of the orbitals. The orbitals which the electrons are occupying in the molecule. So as an example, okay, I'll come to a visualization of the orbitals soon. But before that, what are the limitations of the Hartree-Fock theory? So if you remember that we started with, we assumed that the wave function is a single Slater determinant. So when we solve the Hartree-Fock, we get just one single determinant function as the multi-electronic wave function. So since we are solving it iteratively and variationally, we get only the lowest energy determinant that is possible out of, say, we have m orbitals in a basis, and there are n electrons. So n electrons can be distributed in m orbitals in m combinatorial ways in mcn number of Seyfert determinants. But out of this mcn, we are only taking one. We are getting just one determinant after solving Hartree-Fock. So the rest of the determinants we are not considering at all. So this is one of the limitations, because when we say we are going away from the equilibrium geometry of a molecule, then the other determinants, which are in the space of the MCN number of determinants, they can come close in energy with the Hartree-Fock determinant that we're solving. So the variational procedure is no longer stable. Then we get divergence in the equations, because we try to solve the Hartree-Fock procedure assumes that there's just one determinant. But when there are other determinants which are close in energy, it no longer converges to one solution. And the second limitation is that if you remember that the Fock operator, it assumes that each electron can only feel the effect of all the electrons in a kind of mean averaged field manner. So this averaged field, this simplification, this also fails to account for the movement of electrons throughout the molecule. It's like it sees a cloud of electrons at each time. So this leads to an overestimation. So the energy is actually higher than the actual exact ground state energy. If we take into account the instantaneous repulsion between electrons, it goes closer to the ground state energy. So this is one of the things that other theories which are developed over a Hartree-Fock wave function, that is the post-Hartree-Fock methods, these try to correct this overestimation of energy, and they try to bring it down to the actual energy. I will come to the corrections to Hartree-Fock energy also just very soon. But before that, I will just show you from Hartree-Fock the things that we get. Is it visually useful? So what we get, as I said, we get the electronic wave function. From the wave function, we can visualize the orbitals, and you can see that for small molecules, it is very close to what we actually expect. So we have s orbital spherical symmetric, p orbitals, px, py, pz. Then we have another s-like orbital. So the visualization of orbitals is quite good for Hartree-Fock, at least at the equilibrium geometry of molecules. And it's also good for predicting geometries, the bond lengths, the bond angles of a molecule at the equilibrium geometry. And it is actually quite used also for predicting geometries for the ground state molecules at their equilibrium geometry. And also we can calculate ionization energies, vibrational frequencies, dipole moments, and polarizability, all from the properties of the wave function that we get from Hartree-Fock. Also, Hartree-Fock is also a starting point for application of quantum computing to quantum chemistry. So just like Hartree-Fock is starting point of any electronic structure or multi-electronic structure theory, it is also initial guess for finding the ground state energy of a molecule in quantum chemistry simulations by quantum computing. So for example, in variational quantum eigensolver, Hartree-Fock is used to initialize the qubits in the circuit, and then we apply some ansatz on the VQE algorithm to explore the energy. In the same way, quantum phase estimation, which I will also be kind of going through in more detail tomorrow in the lecture, the quantum phase estimation, the Hartree-Fock method starts as a good guessing point so that we can reach the exact ground state of the Hamiltonian using quantum phase estimation. So Hartree-Fock has a lot of learning the concepts of Hartree-Fock is essential. So if you want to apply quantum computing to quantum chemistry. So now, moving on. As I said, the limitations of Hartree-Fock theory, they can be minimized by taking into account the instantaneous repulsion between all electrons. So the molecular orbitals that we are visualizing just before for the water molecule and carbon dioxide, these are not actually the real solutions, because it assumes that the wave function is just one determinant, and secondly, each electron moves in kind of a cloud interaction with all the others. So it moves in an average charge distribution with all the other electrons. So what we can do to improve this is we take into account the repulsion between each electron, not just average field of electrons. And the missing energy that we have is called the correlation energy. So the definition of correlation energy is basically the exact energy, exact ground state energy, if we subtract the Hartree-Fock energy that we're getting at complete basis set limit. That is the definition of a correlation energy. So since we don't know how to solve the exact energy of a multi-electronic system by quantum mechanics, we don't know the exact energy. But we sometimes can compute the exact energy if we choose a basis. Since we are choosing a basis to solve Hartree-Fock equations, we can find the exact energy. We subtract the Hartree-Fock energy from the exact energy of the basis, and we get the correlation energy. But is there a way to kind of generalize how to solve for electron correlation? So firstly, why it is called electron correlation? So as I mentioned that the single determinant picture and the Hartree-Fock procedure only considers the interaction of one electron with all other electrons at the same time. It is not completely uncorrelated because we have, as I said, a quantum nature in the interaction in the form of exchange correlation. So it has a bit of exchange correlation in it, but the rest of the correlation of each electron is with the repulsion with all the other electrons individually, that individual repulsion is missing. So that is why sometimes the Hartree product is also called the independent particle model. So electrons move independently and the motion is uncorrelated. But as I said, so electrons with different spins, the probability of finding electron 1 at one orbital and electron 2 at other, that is given by this. So this is uncorrelated. The electron 1 cannot see electron 2 just via the Coulomb repulsion term. But with the same spin, since the same spin has a extra quantum characteristic in it, the exchange integral, the same spin electrons can have some sort of correlation in it, which is the exchange correlation. So since no two electrons can occupy the same space due to the antisymmetry of the wave function, same spin electrons are correlated in Hartree-Fock. And this correlation, the exchange correlation K, is the measure of the exchange correlation in Hartree-Fock theory. But the different spin electrons are not correlated at all in the Hartree-Fock model. So what I was saying that since Slater determinants, we only get one Slater determinant using the Hartree-Fock. The other Slater determinants are ignored. So the easiest way to include correlation is we take a superposition of the Hartree-Fock determinant that we have just found out with all other MCN number of determinants. So for a given set of molecular orbitals, the other determinants that can be formed. So basically, Hartree-Fock determinant is the determinant where the lowest energy orbitals are all occupied by n electrons. But we can also generate the rest of the Slater determinants by exciting electrons from one orbital to another. So these electron configurations, if we consider them along with the Hartree-Fock determinant, we can get a correlation. So this is what exactly is done. This is the simplest model for electron correlation. We express the wave function as a linear combination of all Slater determinants that can be formed in a given basis in a given number of electrons. So it's a superposition of, so this is the superposed wave function. These are all the Slater determinants that can be possible in a given basis for a given number of electrons. These are the coefficients of combination. So for a complete CI or full CI, what we do is we arrange all the electrons in all possible ways in all the orbitals that are in a basis. But this usually is scales very poorly with the number of electrons and number of basis functions. To have a handle on why it is so impractical, so about 1 billion determinants is the limit of what the current classical computing architecture can reach. But this also requires highly optimized computer codes. So for a determinant basis, for 12 electrons and 20 orbitals and 10 electrons and 30 orbitals, it's mostly doable with standard computers. So what we need to kind of think now, that since taking account of all determinants in a basis is impossible computation, can we find some criteria so that we can distinguish between which determinants are more important in reaching the true ground state energy and which are less important, or can we truncate the number of determinants somehow? So to truncate the determinants, one concept that we need to understand is, as I said, that how do we form these determinants from the Hartree-Fock determinant? So Hartree-Fock determinants have all the electrons in the lowest energy occupied orbitals. To generate the other determinants, we excite the electrons one by one to other orbitals which were unoccupied in the Hartree-Fock determinant. So we call the Hartree-Fock determinant as a reference, and we excite in all possible ways electrons from the Hartree-Fock determinant and generate the other determinant, which we call the excited determinants. So say the first term is the single excitation. So we're taking one electron, we are exciting it from orbital I to orbital A. Orbital I was occupied in Hartree-Fock, while orbital A was unoccupied in the Hartree-Fock determinant. So we are labeling the occupied orbitals with I, J to K, and the unoccupied orbitals in Hartree-Fock as A to C. So we have singles excitation, doubles excitation. So IJ to AB, we are exciting 2 electrons simultaneously. Then we can excite 3 electrons simultaneously, and hence this goes on till like if there are n electrons, we can have n tuple excitations in the whole data. But we don't want to go to n tuple excitation because basically, if you go to all n excitations, it's like we are trying to do a full CI again, a complete CI. So this is a pictorial representation of the excitation. So single excitation means we are taking 1 electron from here to our unoccupied. We are taking 2 electrons, 3 and 4 electrons together. So this level was where the Hartree-Fock was. These 3 were occupied in Hartree-Fock. This is the single excitation, double, and so on. So for this system, for example, these are 6 electrons. So we could have gone up to hex triple excitation. So we could have taken all 6 electrons and put it in all 3 of the unoccupied electrons. So that would constitute of doing a full slate. So now, what does the Hamiltonian matrix look like after we use, instead of just a single slated determinant, we're taking all possible excitations. So this is what it would look like. So the first term, the diagonal term, will just be the Hartree-Fock energy that we have already got when we had solved Hartree-Fock equation. So this is known. The next one is the interaction between the Hartree-Fock determinant and the single excited. Now the singly excited determinant, the single excited determinant does not contribute with the Hartree-Fock determinant due to a theorem that is called the Brillouin's theorem. So the Brillouin's theorem dictates that Hartree-Fock determinant can never interact with the Hamiltonian with a singly excited determinant. So that's why these terms are 0. So whenever 2 determinants on either side of the Hamiltonian operator differ by 1 excitation, the values will be 0. So the only one that will exist are the diagonal terms and the ones that differ by at least 2 excitations. So we have a non-zero term in the doubly excited, non-zero term between triply and the quadruply and all the others. So this is the general structure of a correlated calculation for a CI hat. Now, how to find the matrix elements? So we get back to the Slater's rule that we had used to simplify the Hartree-Fock equation. So the Slater rule can also be used for calculating the Hamiltonian matrix elements between different Slater determinants. So as I had specified yesterday, for identical determinants, if both sides of the Hamiltonian are the same determinant, the expression is very simple, just sum over all orbitals. Sum over all orbitals, 1 electron term, plus this symbol represents both the Coulomb integral and the exchange integral together. So a double pipe kind of thing. This means that it has both the Coulomb and the exchange within it. So this means MN minus MN. And if the determinants on both sides of the Hamiltonian differ by 1 spin orbital, then as was the case yesterday, the sum is gone. We just have the 1 electron term connecting the spin orbital by which the 2 determinants differ. For example, here the orbital m is replaced by p. So we have just the 1 electron operator connecting m and p. So the orbital by which the 2 determinants differ is only in present here. Also, this one from a double summation, it reduces to just 1 summation, and it is only the orbitals that have by which the 2 determinants phi1 and phi2 differ. So n and p is only present in the whole summation. So using the Slater rule, since we already can easily find out these integrals, and we had also used these integrals to calculate the Hartree-Fock energy, we can construct the whole matrix, the CI Hamiltonian matrix, using the Slater rules. So this is an example of the energies that we get after solving a configuration interaction Hamiltonian. So after diagonalizing, say we are taking only singles and doubles. The percentage correlation energy. So what does percentage correlation energy mean? It means that how close we are getting to the exact wave function, exact energy of the electronic wave function. So the closer it is to 100%, the better the theory is doing. So for example, if you see, when we go from singles, doubles to singles, doubles with triples and quadruples excitation also, we are slowly arriving towards the 100% mark. So as expected. So if we take all possible excitations in a determinantal basis, we gradually approach the exact energy of exact ground state energy of a molecule. Now to have a idea of what is the size of the Hamiltonian, what is the matrix dimension of the Hamiltonian. For just singles and doubles, for the BH molecule, you can see it's around 600. But as soon as we take triples and quadruples, it kinds of grows exponentially. You can see from around 600, it goes to around 30,000. And if we go to the whole full space, that is taking into all determinants possible, the growth of the space of the Hamiltonian, it's actually exponential. So as soon as one tries to solve CI with higher and higher excitations, it becomes completely untenable using our computational architectures. So we could have stuck with solving CI, but as you will hear in other lectures also, we need other theories also to account for electron correlation. And why is CI not enough? So one of the drawbacks of the configuration direction method is it is not size extensive. Now, what does size extensive mean? So consider a 2-electron system like hydrogen. It has just 2 electrons occupying so 2 electrons occupying one orbital and the other 2 electrons. So these are the only 2 possible Slater determinants that is possible for hydrogen in a minimal basis. But say we have 2 non-interacting hydrogens. So there are 2 hydrogen atoms separated by a distance. So this one will have a 2-determinantal picture. So this is the Hartree-Fock determinant. This is doubly excited determinant with respect to Hartree-Fock. The other hydrogen will also have its own Hartree-Fock determinant plus a doubly excited determinant with respect to the Hartree-Fock. So for 2 non-interacting hydrogens, to describe the whole system as a composite, not individually, so it will be like a H4 molecule, we would need quadruple excitations to exactly express this wave function. Because this one is a double excitation, this one is a double excitation, and when we consider this together, it would be a product of 2 double excitation, like a quadruple excitation. But since we are solving CISD here, we do not have the quadruple excitations. So what happens as a result is we don't get size extensivity. Means that when we have a molecule and we kind of separate it into fragments, or we separate it into subsystems, and we solve the subsystems at the same level of theory as the composite system, then the sum of the energy of each subsystem that we get at that level of theory should be equal to the energy that we get from the composite. So CISD energy for one H2 and other H2, if we add them up, it should be equal to the energy that we get for the H4 system. But we do not get it because for the H4, to have it exactly, we need a quadruple excitation. It cannot be found at the same level of theory that we want. So we need to have a CISD TQ to get a size extension theory. So this is a drawback of CI, that if we do a truncated CI, that is we stop at a certain level of excitation, we do not get the size extensivity. And the importance of size extensivity is, say we are trying to calculate the dissociation energy of a molecule. So at the dissociation point, we have 2 fragments of the molecule. And if the size extensivity property is not manifested in a theory that we're using to calculate the energy, then we'll get errors which are kind of far off from the chemical accuracy that we want. So what we need to think is, how can we design a correlation theory which will improve upon the Hartree-Fock determinant and also get us closer to the exact energy, but it will also have the property of size extensivity. So 2 non-interacting fragments, when we add the energies, it will give the energy of the composite. So to do that, the simplest theory that could be done is a direct extension of the perturbation theory that we use in quantum mechanics. So this is, since we are working with multi-electronic systems, it's called the many-body perturbation theory or a molar basic perturbation theory. So why this approach is size extensive, that will come soon. So what the perturbation theory is, just like any classical perturbation theory, we have to split the operator into two parts. One will be, we will call the unperturbed Hamiltonian, the other will be perturbation upon the unperturbed Hamiltonian. So we have a H0 plus a lambda H. Lambda is the perturbation parameter, the strength of the perturbation. We expand the energy, we expand the wave function in orders of perturbation, so 0th order, first order, second order. So, and for the many electron wave function, since we are starting with our starting point is always Hartree-Fock, the simplest unperturbed Hamiltonian is the Fock operator itself. So the Fock operator is what we had used to solve for the Hartree-Fock net. And the eigenvalues of Fock operator are known. So the unperturbed Hamiltonian should always be such in a perturbation theory so that the eigenvalues of the unperturbed Hamiltonian is known. And we already know the unperturbed Hamiltonian's eigenvalues because we had solved Hartree-Fock earlier. So this is the natural choice of H0. So it's the Fock operator. While the rest of the operators, that is the instantaneous electron repulsion between each electron, 1 by Rij, that we are missing, and the two-body part inside the Fock operator, that we are taking as a perturbation. So if I just quickly go back. This was the structure of the Fock operator. One body part, the Coulomb repulsion, and the exchanging. And the original Hamiltonian has the structure of this one. Yeah. So the first, so when we are defining the Fock operator as the unperturbed Hamiltonian, what we are missing here is the instantaneous repulsion between each electron with each other, which is basically the definition of correlation. Also, we have some part that we are missing here. And that is exactly what this Hartree-Fock potential means in the. So this is the missing part that is there in the full Hamiltonian. When we take the Fock operator, we only have one part of the potential, which is basically a mean field potential, and the rest of it goes into the perturbation. So if we solve using classical perturbation theory order by order, each order of correlation energy and each order of the correction to the unperturbed energy will basically be each order of correlation energy. So following the perturbation theory, we have the values here. So let me just sum up without going into the details of the mathematics. The mathematics will be given in the lecture notes that we'll supply you after the conference. So basically, since the unperturbed Hamiltonian is the Fock operator, the action of the unperturbed Hamiltonian on the wave function is just the Hartree-Fock energy of each orbital. So this is the sum of all orbital energies. And this is the action of the unperturbed Hamiltonian on the wave function. The first order correction, which gives the first order correlation energy, is the expectation value of the perturbation, that is 1 by Rij, and the Hartree-Fock potential. And after doing the manipulations, we get just minus half Ij minus Ijgi. So as I said, this notation means that it has both the Coulomb and the exchange integrals. So what we see is this term is exactly what was the expression of the Hartree-Fock energy, if you recall it. Yeah, so this is the Hartree-Fock energy. I sum over all orbitals of one electron term plus Coulomb minus exchange. And this is exactly what we are getting at the first order. So the first order correlation that we are getting from a perturbation theory analysis, it is basically the same thing. It does not improve upon the Hartree-Fock energy. So we actually, at the first order of energy, we don't get any new correlation energy added. This was already present in the Hartree-Fock model. So we have to go to the next order. So at the second order is where we get the first kind of improvement upon Hartree-Fock model. So this is the final expression that we get if we solve for the perturbation theory using Taylor expansion and the normal mathematics. So if you the thing here to observe is that there's a denominator, and this denominator is the difference between two different determinants. So this is the energy of the Hartree-Fock determinant. This is the energy of the other determinants than the Hartree-Fock. We can simplify it further in terms of just the orbitals, and it becomes the difference between the energies, the orbital energies that are that corresponds to the excitation here. So, for example, for the integral ijab, the denominator will be, so AB, if you recall, AB are the unoccupied orbitals with respect to Hartree-Fock, and Ij are the occupied. So this denominator is important because when the other determinants in the mental basis of MCN, number of determinants, whenever the determinant comes closer to the Hartree-Fock determinant, this value will go close to 0. And whenever the denominator is 0, we know that it will diverge. It will go to infinity. So this is another good kind of indication that why the energy kinds of diverges when we go away from the equilibrium for Hartree-Fock based theory. Another thing that we should note is the second order correction is always negative. And since the second order energy correction is negative, we can see that the Hartree-Fock energy goes down, which is what is expected. Since electron correlation always drives down the energy of Hartree-Fock, it goes closer to the exact energy by variational principle, as we know that with the approximate wave function, the approximate energy always is above the exact energy. So what electron correlation, the negative sign implies here is that electron correlation has always a stabilizing effect on the whole system. So to summarize, so basically what I try to give an overview of today is the Hartree-Fock equations, how to solve them, why the Hartree-Fock is, what are the key points of the Hartree-Fock theory. That is, it's a very simple assumption. We can solve it. It has a kind of conceptual clarity in it. It's the first step on which the improvement of the energy so that we can go towards the exact energy is formed. It has a quite feasible computational scaling. It scales to n to the power 4 with the number of electrons in the system. It has some level of correlation in it, of course, via the quantum nature of the exchange repulsion. It is a basis for molecular orbitals and visualizing it for molecules at the ground state in equilibrium geometry. But can be applied to systems, various kind of systems without any additional computational complexity. And the limitations of Hartree-Fock are it does not uh, consider the instantaneous repulsion between each electron. It just considers it as a mean field traveling, one electron traveling like it's seeing just one electron at the same time, just a field. So it kind of overestimates the energy. It has a single Slater determinant wave function, and we saw from the perturbation theory analysis that a single determinant structure can be very poor when we go away from the equilibrium because some other determinants can come close and the denominator goes to zero and it diverges. Also for excited states, just one determinant with only the lowest orbitals occupied at the lowest orbitals occupied with any electrons is a poor approximation. We need a superposition of other determinants, and we also the potential energy surfaces. That means the when we map the energy with respect to the bond distance of a molecule, that will also be poor because Hartree-Fock is a single determinant and the other determinants are not taken into the picture. And then we mentioned a bit about the CI, which is the simplest way of looking at how to improve the Hartree-Fock energy. And possibly in the next lecture, I will try to show you there's a equivalent of a CI calculation, the quantum algorithm framework, which is called the quantum phase estimation, which is just an eigenvalue solving problem. And I will try to show you how the algorithm works and how can we get the eigenvalue of a Hamiltonian exactly for a multi-electronic system using a quantum circuit algorithm. So that is all for today. Any questions, please? Yeah. Yeah. Sorry, Hartree-Fock? Can you repeat? The wave function, yeah. The wave function. Only that one, yeah. Okay, yeah.
Now we see the
Yeah. Yeah. Which one? The excitations. Okay. This one. This one. Okay, even the values, where the values were. Okay, okay. Yeah.
double and triple for each.
Yes.
That's the part why.
So the BH molecule has, probably since these values were taken from, the literature, I guess, it was not present in literature, this value. CISDT calculation was not done. Yeah.
Some water. If there is no more questions, so thank you. Yeah. Lunch. I'm not sure. Uh, then also maybe the graphics will not be, it will not be shown. Maybe. Because I may probably writing on the tablet. Yes, yes. Where in the guest room? Oh, here.
Hello. Full media, okay, so you want to stay here in the lecture. At school, what they do. Then I would start your thoughts, there's you guys, they keep it around. Please, the light is ready, you can come on. So I just think five right out of come. If you don't come for it, the next 5 minutes, you share it today, you get the security period. So please come now, the light is ready. And then those who, please hold on, those who want to be 22, again, when you pick your food, please go there again. Pass your lunch, so calm down, this is slow big time, so tall. Please come move, exactly, nobody's standing up, no one's eating your food.
Ah, Tonya, ya voy a Not bad.
this one too. Ah, so you can't give it. There, what? What the Johnny Cla? Ah, now they see one. I can't make kind of. Boom. Okay. How was your boss? They don't come inside here. Alright. Okay. This one. Yeah. Right, right, yeah, right.
We need a text. Because,
Which of the, this one?
yeah.
Yeah, you will
Read the one day.
Elias QST. Ah,
Say, you get English.
yeah.
Automatically. Find a function in this thing. And take that.
This one. Yeah, you told me. Abi,
Present. And it's not saying, so yeah, the report, any action to be report.
nah. You know who you get. But I don't know why. I will say come.
You. Super machine, the board, the.
What the?
But
Yes. Or step from this people, we can be normal.
Yes. Yes, actually, I hear you right there.
Yeah, not.
Maybe when you say you're meeting you can there's Zoom.
Because if you write on this board, they won't see.
But if they see that, they see.
Yeah,
The
but that
Zoom,
angle is
this
quite
is live
small.
streaming, the Zoom. So you want me to write on that?
Yeah, so there is a notepad on the paper, right?
No, I understand, but let's say if they see, I mean, if they see that, they wouldn't see what is written here. You can't put the camera on this.
On this board.
This board.
Impossible.
Almost nothing is impossible. I mean, he's moving the camera. I see it, right? So
Yes,
can't you?
but
Can't you put it in this direction?
You can put camera on him, but
By the way, Andreas, nice to meet you. Yeah,
Francis.
Francis. Okay.
Let
Do
me
I
get-
do it
let me get
correctly,
it.
roughly?
Oh, yeah, it's
Did
good.
it? Okay.
You did the sound, so it's good.
Okay. No, I see.
There's no sound, there's a problem.
Wow.
Let me get the
Okay, so he's trying to work on that.
Then
And just
do we
put
have
the
do we
camera on
have do we have
the.
pens?
Yes, I put the marker. I think that's also good. I will be But you are four, so maybe that's what happened.
Ọmọ na ń wo inside.
Okay, so catch us like.
Yeah. So, are you going to do projection? Nice.
Oh, yes. You mostly write Charles stuff down, right? But I will also show them a little bit.
Make me this one. Come on.
Now welcome to whiteboarding.
Merci, beautiful. Good one.
So where is the current? Okay. I will have enough. I will have enough battery for that. That's fine. Okay. Should I connect here with the? How do I connect?
So you join on Zoom. Zoom meeting.
Ah, it's a Zoom meeting.
Yeah.
Ah, you
So
look at
you have
this.
the
Okay.
info here.
So, but this means I need a Wi-Fi connection.
No, not this one.
Not this
We
one.
have Max Lab, other networks. The Max Lab.
This one?
Yeah.
Also, physics student or math student, chemistry. Also MS.
I completed my undergraduate last year.
Ah, sorry, so you're PhD students?
Yeah. No, I'm not doing that. I'm doing my national service.
Ah, okay, so you can do your national service in research. Yeah, everyone can apply, but they don't want to run. Okay, you know, yeah, that's good.
Yes. Hey, that is for
Yeah.
That's for the Wi-Fi.
Yeah. Okay,
Meeting ID is 915
915
829
839 82, sorry.
29
829
584
584
84.
84. I repeat, 915
Yeah.
829
Yeah.
584
Yeah.
84.
Yeah.
Okay. Join.
Join. Then passcode
75
71
71
62.
62.
Yeah.
Agree of cases done. It's
Wachezo kwenda makama. Maka odebe chogo.
Mako. Umrana natural.
See, you do me a show. Your choice, what? This how to see it. Oh, I have blame you. Oh, so this online for Zeno Berugo.
okay, and then I can share. I can share and then show my video, so to say, that's it, right?
No, we have Makai. Yes, we shared. You can still use it. You can still use the converter so that you connect this. Use it to the okay.
So this probably I'm loud enough. I will see if I'm not loud enough. I will use it. Can give me. Is this switch?
Yeah,
No, it's
switch off.
oh, it's off.
Okay,
Okay.
that is on.
No, it's on. Okay, so it's on. I see. Perfect.
But it's on my can hear.
Ah, those online has to
Yes,
hear. Okay,
without
I see,
the mic,
I see, I see,
you can't
okay, because otherwise they might hear me.
After everybody. One more thing, first airline checks we're not very happy about. I'm sorry, I have two dozen of you yesterday. That's not my fault. Don't worry, you'll not bring in any soup options going forward. Please look for people like this. So please don't be upset with me. A few, you'll just bring a few, like 5 or 10. Please. Those are what, don't expect a option. So please, you are starting the next session. You can't hear me. Start the next section now. Can you hear me? Please start starting the next session now. So please prepare your mind. Ask questions, which is correct. Let's welcome our facilitator.
Thank you very much, patience. The people in the back, do you hear? People in the back, do you hear me? There's a partner, so there's fine, right? So I'm from the University of Freiburg, and I'm going to teach a little bit about mathematics, or let's say about mathematical backing of quantum computing, right? So at the end, I mean, you have to build these machines, and for this you need material objects, and then you have to do operations on these material objects. For this you need a certain input from quantum optics, right? So now, louder. Okay, yeah. So even with microphones. So whenever you look at the very first thing, if either it's not loud enough, or it's too fast, or both, right? Or just a bad pronunciation or something like this, you don't, because this you don't understand, it's still a sign. So then I would like to start with understanding which is the background. So I already talked to some of you in the last couple of days, but you also see other views. There's no one. So could you please start essentially going from the back and forward, machine, or let's do it like this. Who is
fully grown physicist. Oh, oh, that is. So I know that now this is computational visualization physics, right? And then, so anyway, so I was going. Sorry. We. All that, so it's funny, stress. Physical. No background noise. This is better. And then. Yeah, also computational. Here modeling. What else? Competition. Computational. Maxwell. Maxwell. So he was mathematician. That was mathematician. Well, with statistics, was doing, I don't know, algebra, was doing computational mathematics or computer science. Very much with engineers. So, what did I not call out and is still here? So we have biology, right? We have mobile. I mean, say computer science, right? Computer scientists up.
engineers? Anything else? Anybody from humanities? Arts? Right. So, medicine. So who already has a systematic training in quantum mechanics? Who already has a systematic training in quantum mechanics? Systematic training, like a fully blown lecture in quantum theory. Who had the people already know it? So I believe that. So, and then who did as I say, when you want to build a quantum computer, one of the main problems why a quantum computer is not in the ground because there's too much noise. Qubits cannot communicate in a coherent way with each other, right? And since we want to really communicate here at least for, I'd say, 1.5 hours, right? At last. So now, since it's quite a mixed crowd, I would like to ask you, I mean, it's really intersect, right, or to ask questions when something is clear. I mean, I will start relatively at a relatively elementary level, but still, let's say, since there are also other lectures, of course, I'm trying to complement that. It doesn't make a lot of sense when I talk essentially over your heads, just besides me and to the wall. So now, who has already seen the physical constituents of a quantum computer? Let's say, what do you imagine? I mean, what is the essential building block for a quantum computer? What is a quantum computer composed of? What is the, I mean, when you do a quantum computer, what do you have to do? I mean, you already attended lectures by Leonardo, right? He told you that, I mean, for example, he told you about certain operations on certain objects. And these objects, how do you call them? Quantum bits, right? So then how do you call these, I mean, discrete operations in some sense, which you do in quantum algorithms or quantum computing, which operations do you apply in quantum bits? Unit operations, unitary operations. Okay. Yes, unitary operations. And then if you, for example, apply now unitary operations on 2 qubits, how do you call these typically? Finally, yes, there's another thing that if you want to have a condition operation, for example, how do you call it? It's gates, right? So you want to do gates, right? So essentially, you do operations on single qubits, or you do operations on 2 qubits, and in principle, even. And then how do you call the set of qubits on which the computer works? Like also in classical computing, I mean, let's say when you have these bit strings, how you call they are sitting in a circuit, yes, but let's say just the array of qubits or bits, how do you call it? So what do you say? States. No, you prepare the qubits in states, right? But the array of qubits is just called a quantum register, right? It's essentially a register on which, I mean, you operate, right? So, and how do you imagine does this look like? I mean, let's say, how do you imagine that this much? What's the material incarnation of such a quantum register where you have several qubits sitting next to each other, which then you perform operations or sequences of gates and of unitary operations of single pairs of qubits. How do you think this looks like? Have you ever thought about it? Have you seen them? Look, at the end, somebody has to do it, right? So you have to have an idea of what it looks like, right? So that's why I brought you this picture, right? So we look now first at this movie. So this is what we have here, right? This is actually a quantum register now of 4 qubits, right? And now we see that these qubits, I mean, they actually that's from a high resolution camera in the lab. Or let's say you see the big thing, right?
And so whenever it's bright, it means that the qubit emits light, photons, and the photons are received by its camera, right? And now when a two-level system emits photons, so what does this physically mean? Let's say, I mean, how do you realize a two-level system? What do you need to have a quantum mechanical two-level system? How do you physically realize a two-level system? People don't be, I mean, there's no reason to be afraid of something like this. Just give me a suggestion. Yes. Let's say okay, let's say what do you think is physical? I mean, make a suggestion for the system which should have these two states. So let's say something not actually this. Can be true or false? Yes, right. So now in quantum mechanics language, how would you say that something is true? Or how would you decide that a statement is true or false? Somebody needs to, I mean, let's say it's like two qubits, right? You need to emit a signal which is strong enough that it can be received by the other qubit, which is now the receiving qubit. So again. So what is the quantum mechanical statement? What do you mean by, how do you quantum mechanically decide whether something is true or false? Yes, but now, for example, I mean, indeed, you ask quantum systems, right? And then, I mean, quantum mechanics, the measurement process, quantum mechanics essentially consists in asking specific questions to a system, right? And then either you get a click, then the answer is yes, or you don't get a click, and then the answer is no. So now imagine you have a photon. You have a light field, right? You make it so weak that there comes single photons, right? So now, how would we characterize a photon? So I tell many experimentalists here in the audience, please prepare a photon. So the experimentalist will not be happy because the machine will ask them to be more precise. So what do I have to tell when I say prepare me a photon? So then I have to say a photon with the following properties. Which properties do I have to spell out, such as the experimentalist knows what he or she has to do? Wavelength, Justin, physicist, mathematician, chemist, engineering physics. Okay, applied physics. Okay, wavelength, what else? Yeah, yeah, okay, good. Yeah, what else? The polarization, fantastic. Yeah, very good. Okay, so the polarization, right? So now, when you look for the polarization, in which vector space is the polarization living? So I mean, let's say, what is polarization? Which property is described by polarization of the light wave? Okay, let's say coordinate space, yeah, let's say, I mean, the polarization, which property does polarization describe? Polarization of what? Of the light wave or the photon, the direction, right? Of the direction of the electric field measurement, right? And so then which types of polarization do you have? Polarization vertical, that's all. I will, okay, yeah, okay. So, this you still all linear polarization, or these are like this, right? So we have other types of polarization. You know what another half plate does? Yes. then also if you take, I think it's number 4 probably, but then say what you get, what else can you get? This circular polarization, right? So there's circular polarization this way, then there's linear polarization, and then there's elliptic polarization. So therefore, which will be the dimension of the vector space you need to describe these polarization states? So for vector space, you need orthogonal basis vectors, right? So now we have vertical, we have horizontal. This gives how many dimensions? 2 dimensions, right? And then if you garnish them with complex factors, we can actually also produce a circularly polarized light. So you have 2-dimensional complex factors. Okay, so now some people from using sunglasses from time to time. Who is using sunglasses? Why is a sunglass useful? Because it makes it darker behind the sunglass, so there's not so much light coming. Why is not so much light coming through? Because it's essentially a polarization term, right? So now, let's say in principle, if you have now single photons coming with a certain polarization, you put this polarization filter in this direction, and then you do a measurement by the photon, by transmitting the photon from the polarization filter, you ask this measurement essentially asks the photon, are you polarized vertically? And if behind the polarization filter you have a container which makes it big, right? Then this is the answer of the photon, yes, I was polarized vertically. And if you set a photon there is not the detector does not make big, right? Then this means the photon was vertically polarized, I mean horizontally polarized. Right? So this is the answer no, right? So this means that quantum mechanically orthogonality of state of quantum states is essentially in essence equivalent to saying no or yes when you ask the question. Right? So you need orthogonal states, right? So therefore now to encode a qubit, for example, you need the vertical polarization states E and H, or also circular left, circular right, or whatever. Anyway, something which is associated with states in the vector space, Hilbert space, but which you can conceive as simply as a quantum computation. In 99% of our cases, you can conceive as a finite dimensional complex vector space, which you know from linear algebra essentially, right? And then the basis sets are essentially physically realized by mutually exclusive physical states. That was not the question. I thought that's the question. Right. Good. And so here is now, and okay, so we came from the question, when is the what does it mean now when the atom emits the light, the photon, right? So see. So two-level system now an atom. What would be a two-level system in an atom? So when we have light polarization, right? We have these two states. So we call this, for example, 1, and this call 0. So this would be the polarization states, right? Or also like this would be 1, right? This would be 0. So that's all polarization states. Now for an atom, what would be the mutually exclusive alternatives which you encode them your quantum algorithm? An atom. Who knows what an atom is? Come on. So how do you imagine an atom? People, speak up. I need your input. Otherwise, we don't make progress. So how do you imagine an atom? Who wants to make a suggestion? Who wants to make? Please, somebody makes a suggestion. What? How do you imagine that? What's the structure? How do you describe the structure of an atom? Okay, the structure. So what is an atom composed of? A nucleus, a nucleus, and electrons, right? And so what is the simplest atom? You have, hydrogen. the chemists now, right? And the engineers. So what is the hydrogen atom composed of? And an electron, right? Okay, good. So now we have. See, I was talking too long and falling dry already. So here's the electron, right? And this is going around the proton, right? And so now, how are different states of the, how do you distinguish different states of the atom? I can talk loud enough that you hear me even in the back, right? Okay.
Oh, but we need the microphone for online.
Okay.
That's what.
So how do you distinguish these states from an atom? So what's the ionic states of such an atom? You know, of course, atomic model, right? So now you have certain good quantum numbers like N, L, and M.
When you run the next one,
And do you know what these quantum numbers determine? Okay, so it determines the orientation of the wave function in some sense. So it determines the density of the electron, the probability density of the electron in space, right? And so N is what is called essentially the principal quantum number, right? L is what is called the angular momentum quantum number, and that's the angular momentum projection. It is three-dimensional coordinates, variable coordinates, right? And essentially, now for many purposes, the energy of the hydrogen atom is just actually determined by E equals in suitable units, say, by 2/2 times n squared, right? So for the energy, for example, you don't need to know L and M, right? But let's say N and L and M, they run through a certain range of possible values or integers, right? And whenever either one of these numbers is different, right, then the associated eigenstates are orthogonal. So they are mutually exclusive in the sense of polarization equals to orthogonal, right? So now, but now n can go, I mean, n goes from is equal to 0, 1, 2, goes to infinity if you wish so. It's just an integer number, right? Then L goes, anybody knows the range of L? So it goes from 0 to n minus 1. Right? And n goes to minus L plus. Okay. So it makes sense, right? Because this is the length of the vector, right? And then just depending on how it's oriented or how it's which angle it makes with the z-axis, right? The projection to the z-axis, either positive or negative. So okay, but now obviously, if I do all the possible combinations of n's and l's and m's, right? I get a system with many orthogonal states, not two. So then, how do I make a two-level atom out of a hydrogen atom? Right. So actually that's not easy, right? Maybe I will tell you later, right? But let's say in short, what you have to do, I mean, what you have to do by some experimental tricks is essentially, I mean, say this is the energy axis, right? So that's E. So here's E equals 0, right? So here are the positive energies, here are the negative energies, right? And all these bound states, as we say, so these are states where the electron is really bound by the Coulomb potential still exists, right? They are sitting below, which this here is called a continuum. Yeah, so here you have continuous states. Anybody specializing in functional analysis? Functional analysis? I hear yes. Who's saying yes? Please identify yourself. Ah, okay, very good. So, so then you look into functional analysis. I mean, Simon, in this explains a bit more about the components, different components of the spectrum, right? You have a continuous spectrum, and you have a discrete spectrum, right? Which is so-called Rydberg progression, right? Which gives these energy levels, and you see that you start at -1/2. Sorry. Start at -1/2, right? And then you go, as you go from n to etc., you get ever smaller numbers, right? And you get ever closer, the series converges, has an accumulation point at energy 0, which is called continuum fashion, right? And then what you have to do in the experiment, you essentially have to, you have to contemplate quite a bit. This was for a long time, this was not easy, right? So you have to isolate by some experimental means. You have to make sure that in your experiment, at least on the time scale on which you want to perform a quantum computer, you only talk to these two levels, right? And then you call this level, you call it ground state, and this level, call it the excited state, or also you call it 1, right? And this you call 0. And then you have your isolated two-level atom. But you must never forget that the two-level atom is actually a multi-level atom. It's just that, in the experiment, we try to select and to address only 2 of these infinitely levels. And this is yet another reason why quantum computers nowadays don't really work perfectly well, or they realize, because this isolation of two of the multitude of levels works only for over a finite time scale. Don't hear me. So what should I do? Is this just looking forward or thinking? Like this is better?
Yes.
Okay, so now I have to ask the master of ceremony. So look, I think the volume. Will you turn down the volume a bit? Yeah. Try this.
Yeah, I've done that.
So 1, 2, 1, 2. It's better like this.
You speak loud and the microphone down.
Like this. Like this. Does this work? What? That sounds good in my phone. Okay, yeah, good. Can you do that?
Yeah.
Okay, perfect. So people online, do they hear me? Check. Okay, you know.
Yeah.
So now it's better. Very good. Look, you have to say this early, right? Otherwise, you need it 2 hours. Now after the 2 hours, then I mean, it's nice that you're only 5 minutes. Look. Okay. What I was saying, right? So you have to identify your two-level system, right? And one of the reasons why, let's say, many of these computers don't really work well yet is that actually this isolation of 2 levels out of a multitude of levels in an atom is actually working only for a finite amount of time, and as you go longer, right? Other levels kick in and they spoil your calculation. Very well. Okay, good. So now we are still at the question. We're still at the question. So we still have to come back to that. How can I get back to my, right, so all is fine, don't worry. How do I get back to my projection, to this something? Show. Give me patience. So to go back to my
Slides.
to what I wanted to show, the movie what I wanted to show. Yes. This one? Bravo. Yes, I know. Yes, so share. Okay, so now I'm back here, right? So now what does it mean when I now we have our two-level system, right? We have a two-level system, and we are in the excited state, we are in the ground state, and when our light comes out of the atom, right? And now I detect the photon. So h bar omega comes out. H bar omega, what does this tell about which property of the photon does this express, h bar omega? Oh, frequency is omega. What is h bar omega? The energy. Okay, so that's the energy of the photon coming out, right? And so if I detect this, why did it go away?
I think, because you're on the.
Sorry. Yes, okay.
So if you want to go back, I'll just.
Yes, please. So if I detect that, right? If I detect the photon, it means that the atom must have been in the excited state before, right? Because in the ground state, it cannot be the photon, right? So whenever it's right, it means that the atom is essentially going to the excited state. So now if it's bright, then you can say, okay, the atom was in the state 1, right? When it's dark, the atom is essentially sitting in the state 0, right? So that's how we read out. I mean, you run your quantum computer on this quantum register, right? And then you want to read out the result of the quantum algorithm. So you have to infer the state of the register after the operation of the quantum algorithm, right? And that's this kind of pictures how we read that out. So essentially, you look at them. Bravo. Thank you. Bravo. Now, that's fine. And now you will see. I will now switch it on, right? And then you will see that's a real movie from a lab already quite some years ago, right? And so this was in the early stage of building these quantum computers. Now, just actually with trapped ions, right? With trapped a string of ions. You see time is running, right? And at the moment, all of them are bright, but then now we'll see how it's switching between different states at some point. Wait a minute, you be patient. Now, it will come. People experiment with patient. Now you see. Okay. Now it's switching states on the output, right? And so you see, this would be essentially the quantum register as it's interrogated by the experimentalist upon execution of the algorithm, right? And so being in 0 or 1 would be your computational basis in which you read out the output state of the algorithm. And so what we try to do a bit is now to understand, right? So now what is this two-level atom? I'm claiming that you already have seen the generalized state of such a two-level atom in one of the other lectures. So which is the abstract space, or which is the abstract geometry of such a two-level atom? Any geometry. So you saw already a geometric beast according to one of the beliefs. Lost your blah. So name this. Winner. Okay. A mathematician, physicist, whatever. So what's lost here, right? And so essentially, let's say, but how do you do this operation in the block sphere to get from the ground state, from the state 0 into the state 1? Or into a Fourier superposition between both states? How do you get there? Which now in terms of gates, which gates do you have to apply to get from ground state 0? How to get from ground state 0 to the excited state 1? Now, which operation do you have to apply to do that? A polygate, right? So now, which operation do you have to apply to get from here to here? Hadamard, right? Okay. So, and now, how do you do that? How do you implement physically a Hadamard? Did you see that already? Okay, so that will be okay. So then that's what will occupy us today, and maybe also next time. We'll see how we come. Okay. Okay. Still, I want to show you one other picture since we are maybe wait. So I was told I will teach until 4 o'clock, right? But in between we do a little break, right? So when do you want to break? At 3 o'clock, say this is fine. No objections. Too late? Fine, good, okay. So, okay, good. Let us see. I want to show you one more thing. So just to get you an impression, a little bit of what you can do nowadays. So this now, what I'm going to show you now is, let's say you saw here before, you saw a one-dimensional quantum register, right? Where, so say the ions are sitting in one dimensional row. This is a little bit future technology, so it's first because let's say we are able to isolate these single quantum objects only since the early 80s, around 1980. This was done the first time with ions, right? So you have actually essentially used electromagnetic fields to store these ions, right? And then also people at the same time started to isolate single photons in cavities. So what is a cavity actually? Of course, the photonics people have an advantage, but how do you imagine a cavity or a resonator? Resonator maybe resonates more what it usually is. I mean, who also already has heard the term cavity? Passing through a slit to get into the cavity. Yes, but let's say what defines a cavity? You don't know. So the essential setup for a cavity, right, are two mirrors, right? So you put a mirror here and a mirror here, right? And then this gives you a certain mode structure, like boundary conditions. You do your maximum equation or something like this, right? And this defines a certain standing wave, right? Because the wave is reflected coming back, so they superimpose, and then you get the standing wave. And so the position of the mirrors identifies those standing waves that fit between the mirrors, right? You know the Helmholtz equation. Everybody knows the Helmholtz equation from electrodynamics. Anyway, right. So a cavity is something to store photons, right? So storing individual atoms, individual photons was only done in the 80s, 90s of last century, right? And then you slowly start to put them together. And first, you can put ions in a row. But now when you have them in a row, right, you still have these other dimensions in three-dimensional space. And so nowadays people are trying to assemble qubits, ions, individual atoms, actually in two-dimensional and three-dimensional arrays, right? And we'll show you now just such a picture of how people reassemble in real time this arrangement of different atoms. I have to again click here.
Well, we do this after the break. It takes too much time now, so we do this later, right? Okay, so now we start with the real stuff. Okay. Good. So I go back to Blackboard. Whiteboard. One important thing which I still forgot is to say that, I mean, you have different types of two-level systems, right? So you have, we had two-level systems. Now you can take notes. But what I will do, I don't have notes specifically for this lecture series. I have handwritten notes, right? Let's say, but I have some manuscript which I once published with a colleague, right? On very related stuff, which I will probably make accessible to you here, right? Right. So now two-level systems. Physical realization. So we already had photons, and more specifically, specific degree of freedom, which characterizes the photons, right? Their polarization. Yeah. So vertical, for example, you can write it like this: one, up, or excited, right? Or horizontal, this would be 0, or ground state, if you wish so, in the atomic language. Then atoms. So this would be excited state, or ground state. Excited state. Okay. 1, right? Or ground state. 0. Right, and then this bullet here, it means that the electron is in the ground state or in the excited state, right? So in many level atom in either one of two selected levels, right? And then, I mean, since let's say there's another brand of physicists who are even more than the opticians and the atomic physicists together, and one of them is sitting here, solid theta, right? So when you, let's say, when you talk to different brands of physicists, right, and you tell them you want a two-level system, they might have different immediate associations, right? A photonics person will think of polarization equation, an atomic person will think of atomic energy levels. And solid theta, Daniel, you correct me if I'm saying something wrong, but at least my picture of the solid theta is their world is made by double world potentials. So solid state. Right, and then you have, I mean, let's say you can have different ways to realize your two-level system. But one way is, for example, you have your state on the left, your system on the left, right? And the other state would be your system prepared on the right, right? So this would be, and also this would be, let's say, let's call this 0, call this 1. And so there's an entire zoo of how you would, not a question. Okay, fine, yeah. So, okay, so there's an entire zoo of how you create two-level systems, just depending on the concrete physical setting you have in mind, right? Here for a moment, right? So actually, yeah, maybe one question: why is this an interesting object for solid status? Do you have an idea? It's double world potential. So in principle, what you can do, you can concatenate these. I mean, say when you have a solid state, you want to have a lattice, right? Yeah, but in principle, you see that if you essentially just take one of these unit cells here. Let's do it like this. You have a two-level system, and then you concatenate them, right? By this, you can explain essentially the level structure of the conducting across latches. So, okay. Right. Okay, so now just to fix terminology, I will write down the. So you have seen already, I assume, I mean, since you gave me already corresponding answers, so I will use the Pauli matrices. Pardon? Getting out to see? Yeah, okay. So I try to write here. Okay, good. So somebody knows how to run this thing here?
Right one.
Yeah, I will try now. Probably because they are fading away.
So please can you stop sharing?
Yes.
Okay, so yes, your screen can still be there.
Is it okay? Can okay, it works. Okay, so you will see that. Okay. Yeah. Okay, so now we need some ingredients. Is this readable? Well, I'm sorry. Yeah. So okay, I try. So I define now in my vector space, I will define E, the excited state of my atom, myself being an atomic physicist, as 1, as the vector 1, 0, right? And G equal to 0, I mean, identified with the 0 state as 0, 1, right? And now I have several, now I want to induce this transition from the ground state 0 into the excited state 1, right? And for this, I need to act on the atom, right? Because first I have the naked atom, and the naked atom has a Hamiltonian of the I write now naked atom. So it's alone, there's nothing acting on it, right? It's just the atom with these two levels, right? And this is called, I will call it H atom, right? And that's given by what? You have an imagination. How do you describe a two-level system? The energy levels, the two eigenstates of a two-level system in terms of Pauli matrices. You still understand me in the back? Am I loud enough? Am I loud enough? So how would you describe a two-level system in terms of Pauli matrices? It's eigenstates. By sigma z, okay, or by the z Pauli matrix, depending on how you learn that. So write it at 1/2 omega times sigma z. Did you write sigma z or did you write capital Z for the Paulis so far? Did you write capital Z? Okay. Okay, so then I write here. So sigma z equals z equals 1, 0, 0, minus 1. Is this readable? I can see. Okay, if you cannot decipher, please let me know. Shout, right? And sigma x equals 0, 1, 1, 0. And sigma y equals 0, minus I, 0. Right, and sigma x is often in quantum computing jargon is also simply written as capital X, and sigma y in quantum computing jargon is often written as capital Y, right? And then we need two more. Can I move this up? Does this scroll? Wait, how do I? Okay. So still, let me write sigma is defined as 1/2 of sigma x minus I sigma y. That's 0, 0, 1, 0. And sigma plus, right, is 1/2 sigma x plus I sigma y.
and that's 0, 1, 0, 0. Pardon?
Yes.
I never write a minus. I don't write a minus. Yeah, but anyway, yeah, okay, I can write a minus. But anyway, so okay.
So these objects you have already seen, right?
So now, wie scroll ich hier runter darauf? Keine Ahnung. Schauen wir mal. How do I get down on this? What's the
Use this one to screen.
this one?
Yeah.
So
Use
use
the
this
same pen, yeah.
I know.
Mhm.
Ah, bravo. Okay. Good. Thank you very much. And now,
Use the pen.
okay, I see. Okay.
Yes.
Thank you very much. Thank you. Okay. So now let's just convince ourselves, right? So now you have this atomic Hamiltonian age atom, right? On the excited state, right? Which I had defined above. That's why I don't like these things, because you cannot, I mean, easily, cannot keep in under your eyes what I did, right? So I'm acting now with this Hamiltonian age atom on the excited state 1, 0, right? And so this then this gives essentially 1/2 omega times sigma z is 1, 0, -1, right? On 1, 0. And this gives 1/2 omega times E. Sorry. How do I take it away? Probably like this. Okay, I'm learning. Zack. Omega, no, not learning. And omega times E, right? And H atom on the ground state in the corresponding level gives you -1/2 omega times G. Okay, so you see that the energy eigenvalues are spelled out here by this equation. So E is the eigenvector of the naked atomic Hamiltonian to the eigenvalue 1/2 plus 1/2 omega, and G is the eigenvector of the naked atomic Hamiltonian to the eigenvalue -1/2 omega. Right? And now I also need the action of sigma on G, right? Which was this combination of sigma x with sigma y. Sigma was given by 1/2 sigma x minus 1 minus I sigma y, right? So that's not 1, not. And now G was 0, 1, right? And so this gives, you see, so this gives 1, 0. Sorry, there's a plus missing here. So there's a sigma plus on G, right? It's like this, right? And gives me the excited state. Yeah. And likewise, sigma now, which is sigma x minus I sigma y on E, right? Gives 0, 0, 1, 0 on 1, 0. And this gives 0, 1. And so this is G. So this is now just the elementary operators which we need to then build up our total Hamiltonian of which describes the atom and an external agent which acts upon the atom, which will be an electromagnetic field, right? And now sigma this, yeah, and then importantly, sigma plus on E, right? This gives actually ... This actually gives 0, 0, which is the neutral element in the vector space, right? And likewise for sigma minus sigma, okay, sigma on G, also 0, 0. Yeah. So this means you cannot move with these operators sigma and sigma plus, you cannot move out of your vector space, which is just spanned by these two states G. And now you want to mediate or to induce a transition from the ground state to the excited state. Okay. Okay, so now, and as I said, we saw before, I mean, phenomenologically, if you wish so, that if the atoms are in the excited state, they emit a photon, they are bright, right? So there is a, let's say, apparently, if you couple the atom to a light field, you can induce transitions between the excited state and the ground state, right? And so now the idea will be that you actually couple, or you inject a laser light, or at least electromagnetic radiation upon the atom, right? Such that they interact, and that, for example, then the atom can absorb a photon to make a transition from the ground state to the excited state. Okay? So, and now when I describe the electromagnetic field in terms of photons, then how do I describe which familiar physical object, actually in classical mechanics, is then equivalent to the electromagnetic field? You know that. You know that they have seen that? Quantization of field? Yeah. So, so do you know what are creation and annihilation operators? Creation and annihilation operators. I just write the terminology: creation or annihilation. Operators. Has somebody seen that already? Terminology? Okay. So let's see. How do we build intuition? I mean, okay, so when you want the atom to absorb an electron, to absorb a photon, right? So the electron bound to the nucleus should absorb a photon. What will the electron gain then by absorbing the photon? Will it absorb energy, right? So now we have 2 degrees of freedom, right? We have the degree of freedom of the electron, which is bound to the nucleus, right? And we have the other degree of freedom, which is the degree of freedom of the electromagnetic field. So now, do you know an example from classical mechanics where you inject energy, where you pump energy into a degree of freedom which is initially low energy? You know an example? Yes, but that's already quite advanced, and it's not classical mechanics, right? So it's not your everyday life experience. So in your everyday life experience, so for example, let's say when you're on the playing ground for kids, right? There is an instrument, I guess, I'm sure also here, right? I think it's global, where essentially, I mean, let's say you start moving. Swing. I mean, just think where you sit, right? You go like this, right? Right. So then you see that you have to pump energy into that, right? And so that's, I mean, what the mathematicians call pendulum, right? In the abstract way, right? So now, what is the equation? What a pendulum looks like when you are locally, when you only have small excursions of the pendulum. You know what then the force is which acts on the pendulum when it's displaced from its equilibrium position. Is it linear or is it quadratic, or how does the force increase with the excursion? Yes. That's an answer? No. No. Yes. Okay. That's angular momentum, but let's say if the displacement, now you take the angular displacement, right? And so how does the force increase with the angle? It's linear, right? And what is the linear? So you have mx2 dot, right, equals minus, because it's going directly to back, right? It's minus kx. So that's the equation for which object? The linear restoring force. So how do you call this object, which is described by a linear restoring force? How is the potential landscape then? If the force is linear, then how is the potential going as a function of x? The energy as a function of x?
force is the gradient of the potential, right? So to get the potential, it means you have to integrate force over position. So now you have a linear force, or it depends linearly on the position. So then if you integrate that, you get what? Integral x dx gives roughly what? Integral x dx gives what? Integral over x dx. X squared gives something like x squared. It is the quadratic, right? It's the quadratic potential. And what is the quadratic potential? What is this? What is the famous physical object which is associated with that? Look, if you know that, right, you can do essentially all quantum optics. I mean, I say I'm a complex, I'm a many-body person, right? So to me, quantum optics is essentially the physics, quantum physics of quadratic potentials, which is what is this? Yes, but what's more excursions, it's what it oscillates, right? And now when it's quadratic, it's a harmonic oscillator, right? It's a harmonic oscillator, right? So you can show when you do electrodynamics, when you do the quantization of the electromagnetic field, right? You can actually show that the single mode of the electromagnetic field between two mirrors in a cavity, that's how you isolate such modes, right? It can actually be described as a harmonic oscillator, right? So therefore, now you have right, but still, sorry, I'm coming back to my story. So we have a stream. How do you call it? System. Right? So you want to pump energy into that, right? So now, for the smallest version of the system, it's looking like a harmonic oscillator, right? Now you drive the harmonic, so therefore, when you want to pump energy in, you drive the harmonic oscillator, right? So everybody has seen driven harmonic oscillator, right? Yes. No, okay. So now, what do you have to do to drive the harmonic oscillator such that you can transfer a maximum of energy into the harmonic oscillator? What do you have to do? How do you have to drive it? Which condition is that? Which condition do you have to fulfill? Yes, you have to apply force, yeah? But now, let's say, I mean, there's a stream, right? So now you just apply the force, so the stream will externally just keep it, right? But then nothing will happen. Now, but what do you have to do for the stream to go to higher and higher experiments? Say, so that the force you are giving, that the stream is really picking up this energy such that it's really to lift up, to go to ever higher experiments. So how do you have to say, look, I have to get rid of the microphone, sorry. Now let's I'm coming back, I think, right? So this means I have my heating period has to synchronize with the typical time the pendulum goes east to go there. So how do you call this kind of synchronization? Harmonic synchronization, not quite, yeah. So, but you need a force which has to fulfill which condition with respect to the unperturbed motion. Frequencies have to fit. Now, when frequencies fit, how do you call that? Resonance. Who said this? Bravo. Taylor. Mathematician. So why do the engineers know that? Are you building bridges? How you should build bridges, right? So there's now that for building bridges, there's what is called the resonance catastrophe. So that's why the military don't let them know, right? So because you go in resonance, when you go in resonance, that's the optimal point to transfer energy from one degree of frequency into the other, right? And that's what you do all the time when you actually run a quantum computer, right? And for example, now in terms of quantum information, right? For example, you want to store quantum information in a certain physical device, right? And now, what do you think is good for storing quantum information? Which physical objects are good for storing quantum information? We have solid state, we have atoms, we have photons. So who thinks that photons are good to store quantum information? Let's say to store the information, put the photon somewhere, and then read the information out again. Okay. One. Okay. Who thinks that atoms are good for storing quantum information? And who thinks that solid state is good for quantum information? For storage of quantum information? Okay. All the others abstain. This is fantastic democracy, right? So in general, people say photons, I mean, they're actually not so easy to keep somewhere, right? To trap, and they tend to fly, so therefore they are not so good to store quantum information, they are good to transmit. While atoms, also solid state devices, may be good to store quantum information, because if you can find an atom where, for example, the excited state does not decay spontaneously too quickly, you can store it there quite some time, right? And people are actually working on it. Okay. So we know we have a harmonic oscillator, right, which is our swing, or which is our two-level atom, right? And we want to drive it by a periodic force, which is now given by our oscillating electromagnetic field. And so now we write down the Hamiltonian for the quantized electromagnetic field. So let's say, yeah, second ingredient. Quantized electromagnetic field. Yeah, and in the future I will just write EM for reasons of brevity, right? And second ingredient, quantized electromagnetic field. So of a single mode. And we had seen earlier today, right, that the single mode is characterized by its polarization, then by its wavelength or its frequency, right? And then also still by its direction, which is the direction of the wave vector. The wave vector is a vector value quantity which gives the direction along which the waves propagate, or along which is, I mean, the direction of the wave vector also is orthogonal to the nodal lines of the standing wave field, for example, in the cavity, right? And so the Hamiltonian is I write it harmonic oscillator for the field, because we know that the electromagnetic field is a harmonic oscillator, right? And I write it now in quantized form. I write it as h bar omega times a dagger a plus 1/2 times the identity. Yeah, we're now so that's my Hamiltonian. That's the energy of the harmonic oscillator, quantized harmonic oscillator, right? That's the frequency, right? And now, let's say, have you already seen this expression or not? Has anybody already seen this expression, or nobody has seen it? You have not seen it yet. Who has seen it? Please give me a feedback. Who has seen it? Nobody. Okay. Good. So then, how do we? Let's try to make sense how we have to interpret that, right? So we need a break. Yeah. So this is the frequency. H bar is H bar, right? And we still have to identify now these strange objects, A, dagger, and A. Okay. So now harmonic oscillator is this. Okay. So that's the potential. That's the quadratic potential. Okay. And now, if we quantize the quantum states in such a potential, you know that a quantized system in a binding potential then only admits discrete eigenenergies. Okay, this is plausible. Is this plausible? Yes. No. Yes. Okay. So then we call this n equals 0. This we call n equal 1.
n equal 2, and so on. N goes here now in this case goes from 0 to infinity, okay, through the non-negative integer numbers. And n equals 0, that's important for the terminology. This is also called just simply, sorry, no, we cannot use that. We have to write differently, like this. No, not 10. Yeah. Yeah. This is also the vacuum state. Yeah. So that's the vacuum state. Yeah. Which means that, right? So you see that the minimal energy of the classical system, this would be the classical equilibrium. Classical equilibrium. Yeah, or ground state, right? So if the oscillator is just has no energy, right? Just staying like this, right? But now quantum mechanically, you cannot realize that, right? So you have a finite minimal energy, and this finite minimal energy is the energy of the vacuum state, right? And it's actually just so the energy of n equals 0 is actually just 1/2 h bar omega, right? And the splitting between these levels is just omega. Okay? Because actually now I will define the action of these operators. So for reasons of time, I will not have time now to explain you how you really derive the action. I just have to state it now. So so the action of these operators let's put it like this. So A dagger upon an eigenstate n. So now this state here is an eigenstate of the harmonic oscillator, right? So it's one of these energy eigenstates, right? And now I write down what is the action of A upon each of these energy eigenstates, right? And so A dagger, yeah. A dagger on n equals square root of n plus 1 times n plus 1. And A upon n equals square root of n times n minus, times n minus 1. Okay. So now my question again, I asked again, maybe you had seen it already, you just didn't remember. Who has already seen that? Somebody already seen this? You have seen it, anybody else? Okay. Okay, such that then A dagger such that A dagger A on n equals what? Then now I know that somebody has already seen it. So what is what comes out here? If I let A dagger n act upon n, what comes out? Just make a suggestion, but please loudly so that I can hear it. Okay, so this gives actually n times n. Okay. So therefore, this object here is also, sometimes it's also written like capital N, and it's called the number operator. Number operator, the counting operator. It counts how many excitations are in your quantized field mode, right? And what's the name? What's the name of these excitations of the quantized field mode? What's the name? How do we colloquially call them?
Actually, follow my question. How do we colloquially call the excitations of the quantized harmonic oscillator? How do we colloquially, so in everyday physicist language, call the excitations of the energy excitations of the harmonic oscillator? You want suggestions for position? No. Excitations. So what do we know about, let's say, what did Max Planck discover? Planck's constant, right? So, and what did this, what does Planck's constant suggest actually? Is energy a continuous quantity or not? It's one side. So now, what are we looking at here, right? So we are looking at the energy of the harmonic oscillator. Sorry, I'm really not yet very fluent with this device. We are looking at the energy of the harmonic oscillator. It's quantized, right? The harmonic oscillator is representing the energy of the electromagnetic field. So therefore, the quantized energy levels of the electromagnetic field are the energy units. Are the possible excitations of the electromagnetic field. And how do we call them? Let's say, does the energy in the electromagnetic field come in continuously, or does it come in small units? And how do we call these small units? Discretization, but for the electromagnetic field, how do we call them? The electromagnetic field is, what do the G-Pol people make experiments with? With photons. Did I hear this? Yes, and photons are the single excitation of the electromagnetic field, right? So the excitations, this counts the number of photons in the field, right? So a photon is nothing else but the excitation level of the harmonic oscillator, which represents the quantized electromagnetic field. That's what we mean by a photon. Okay. So saying we have two photons means that we have prepared the harmonic oscillator or the electromagnetic field in a state which is the second excited energy state of the quantized harmonic oscillator associated with this mode. Okay, so that's what we mean by a photon. Yeah. So, right, and so now, therefore, finally, we can write down. First, we have to move. So now we know. Look, we know now. Here's the Hamiltonian, right? So I have to take this away again. Anyway, so here's the Hamiltonian: h bar times omega times a dagger a plus 1/2. So we know how a dagger a acts on the eigenstates of the energy operator, right? And so therefore we know that a dagger a on n gives n. Yeah, this 1/2 times the identity gives just 1/2 times n, right? And so therefore we know now the eigenstates also, the numerical value of the eigenstates of the quantized harmonic oscillator is h bar omega times n plus 1/2, right? So therefore the eigenvalue equation for the quantized electromagnetic field is HO equals h bar omega times a dagger a plus 1/2 identity, and so HO on n equals n times h bar. H bar omega times n plus 1/2 times n. Okay, so therefore E n harmonic oscillator equals n plus 1/2 h bar omega. Okay. What's the time? Okay. So, and now, let's say now in a minute we do a break, right? But now we have this Hamiltonian, right?
remember that we have also the atomic Hamiltonian, atomic, right? This was 1/2 omega sigma z, I think. Yes? Yeah. And now we need to couple them, right? So now we need want to couple atomic and the electromagnetic degree of freedom. Degree of freedom, yeah, which I will also write as DOF, yeah, to induce dynamics of the atomic qubit, such as, and dynamics would be such as, such as Hadamard. Yeah, what we want, right? Let's say if we have, now I try to depict the Bloch sphere. So if we have here the coordinate system, right? So we have x, y, z, right? So then we have the Bloch sphere, which is something like, I try to do it like this. So, right, and say here is the, here is the, here is the ground state, and here's the excited state. Yeah. So then, for example, we want to go by Hadamard. For example, we go from here to here with a Hadamard, right? So such that h upon 1 gives me 1 over square root of 2 times E plus G, right? And we want essentially to see how by coupling now the atomic and the harmonic oscillator degree of freedom, we can induce the atomic degree of freedom in this kind of method. Okay? And that we will look at after the break. So we make a break of, I don't know, 10 minutes maybe, and 3:30 we start again, right? Okay, sorry. Come. It's not good, right? Because everything is disappearing again.
Yes.
I want to couple the atomic and the electromagnetic degree of freedom to induce the dynamics of the atomic qubits, such as, for example, the Hadamard, right?
Okay.
So now we want, let's say, we have the harmonic oscillator, which describes the field, right? And we have the two-level atom, right?
Okay.
And now we have the two-level atom describes the atomic degree of freedom.
Yeah.
The harmonic oscillator describes the field degree of freedom. But so far they are not coupled, right? So it's like a swing, right? And somebody is pushing in the other direction. Nothing is happening, right?
Okay.
So now we have to couple them. So, and that's what I want to do next, right? And two, with the purpose, right? By this coupling, let's say, so look, if I prepare the atom in the excited state 1, and I have no external force, it's an eigenstate. It will not move in time. It will stay there.
Yes.
So therefore, if I want the atom to get from the excited state into the superposition, I have to act upon this, and I will do it with the electromagnetic field, right?
Okay. Yeah.
But still, I have to couple them, and I want to see how I have to apply this coupling to get at the end this Hadamard gate, to realize this Hadamard gate. Okay?
Yes.
Yes.
Thank you.
But is it trivial? Is it too slow? Is it
It's moderate.
okay? Cool. Very good. Ja, denke schon. Ja, obwohl danach ist der Leonardo, glaube ich, ne? Im Vier. Ne? Ja, ich höre mir das noch an. Im Moment ist es nicht so, was der so macht. Ja, ich wollte auf jeden Fall zurücklaufen. Ja.
Jetzt macht es
Was ich gesagt habe. Ja. because the money quality. Yeah. Ja, nicht, sie also, wir haben eine Urteilsfähigkeit.
Okay, everybody refreshed. Everybody has enough water, not dehydrated. Okay. Okay. So where are we, right? So we have seen we have 2 degrees of freedom. So on the one hand, we have the degree of freedom of the qubit, right, which is one constituent piece of our quantum register, on which we want to implement run a quantum algorithm, right? On the other hand, if we were to prepare the qubits either in the excited state or in the ground state, so in 0 or 1, right, and have only the Hamiltonian of the qubit, then what will happen? Nothing will happen because the excited state and ground state are eigenstates of the energy Hamiltonian of the qubit, right? It is an eigenstate of the energy Hamiltonian of the qubit under the dynamics generated by the unitary, which is generated by the Hamiltonian. You just remain in the state where you are, right? You just pick up a phase e to the minus I times E j, where j is either 0 or 1 times t over h bar, right? And nothing else happens. So the projection, the excitation value to be in the excited state or in the ground state, if you prepare the system in the ground state and the excited state, remains invariant equal to 1. So therefore, if you want to make the qubit move, right, in the Bloch-Spear language from either one of the poles to the equator, you have to induce some dynamics, right? And this is like when you have the scissor, right? Scissor, when it's either, either when you want to stop it or when you want to make it move, right? When you want to stop it, you have to break it somehow or make it slower, right? You have to extract energy. Or when you want to make it move, you have to inject energy, right? And so therefore we already have the intuition from what we know about the driven harmonic oscillator that we have to drive the system here, the qubit, right, by a force which is periodic and which has a frequency which is close to resonance with the unperturbed motion of the scissors, or in our case of the two-level system, right? Now, the unperturbed frequency of a two-level system is just given by the energy difference, right, which I will call small omega, lowercase omega, and the energy level difference of the harmonic oscillator, right? Is just given by integer value by 1 times h bar omega. So, and the frequency I will call it kappa. And so resonance condition, which I intuitively expect to be useful, right? To optimally couple the light field to the atom, means then that lowercase omega is equal to capital, right? Is similar, right? So that's what we want to do. But still now we have the Hamiltonian of the electromagnetic field, of the quantized electromagnetic field, so which can have a certain number of photons, right? And the photons are what? The photons are just the excitations of the quantized harmonic oscillator which represents the field, right? And we have this Hamiltonian, but they are not yet coupled. So let's say, if I had a swing, right, which is sitting here, and I have a force which, for example, goes in this direction, but the swing is going in this direction, right? Nothing will happen, right? So I need to somehow couple the two, right? And so therefore I need, let's say, if I now describe the quantum system composed of the harmonic oscillator and of the atom, I write the joint Hamiltonian will be just the sum of these two Hamiltonians, right? And so because the Hamiltonian is the energy operator, right? And if I want to calculate the energy of the atom and of the field, I just have to sum them, right? But now I still need on top the coupling, right? So let me see. Yeah, and the aim of the coupling will be then later that we can deterministically move the system, for example, transfer the system, the qubit, for example, from the excited state into a superposition, balanced superposition, as I said, between the excited state and the ground state. And so now, so we still need a coupling. And here now, I write first the coupling in a classical form. So now the idea is a bit the following, right? So, I mean, you have idea. No, sorry. Okay. Idea. Couple the atom and the field. And now the atom is something like, you see, you have this nucleus, right, with a positive charge, and then you have the electron, which is circling around the nucleus, right? And so this is just a picture, let's say a classical picture of the electron circling around the nucleus, right? And now the electron would be, for example, here in the excited state, say 1. Yeah. So that's essentially the orbit, right? For the chemists, right? You will always see these in chemistry. Often you see these orbitals, right? This now is a picture for one of these orbitals. And now, what do you have when you have two charges of opposite sign which are displaced? What do you then create? Dipole. Right? That's a dipole, right? It's a dipole, and now the idea is, okay, now I place this dipole, the atom, into an electromagnetic field, right? So then I calculate as a coupling, the coupling energy between the atom and the field. I calculate this as essentially the energy of a dipole in a electromagnetic field. So this I use from classical mechanics. This intuition I use from classical mechanics, or from classical electrodynamics, sorry. So the energy of atom in an oscillating electromagnetic field. Yeah, and now I take the oscillation to be a simple cosine time dependence. So I write that as I write this coupling operator as V, right? That's the coupling operator. Right? I call this V, and I call this the negative charge of the electron, right? Elementary charge E. Then the amplitude of the field. Then the position of the electron in a one-dimensional space, so in the x-axis with respect to the nucleus, the displacement of the electron with respect to the nucleus, and then cosine omega t, right?
And I assume that now here I wrote F, this is the amplitude of the field. Amplitude of the electromagnetic field. Now I choose that, of course, it's associated with a vector, electric field vector, right? That this field vector is parallel to the x-axis of my three-dimensional space, and that also the k vector of the field, so this is the wave vector of the electromagnetic field, be parallel to the z-axis. Okay, so it's a wave propagating in z direction, right? Or I mean, let's say with nodal lines which are perpendicular to the z-axis, right? And so since it's a transverse wave, so the field vector will oscillate along in the transverse plane, and I fix that the direction of the oscillation of the field vector along the x-axis, right? And so now one has to do a step in this language which we use, where we describe the electromagnetic field also in this quantized form, so that the electromagnetic field is composed of photons, single excitation of this quantized harmonic oscillator. I have to translate that this interaction part of the Hamiltonian, right? I have to translate that into quantized language, or the second quantized language, quantization. Because what I wrote here, right, this is actually what you would write in a classical description of the electron sitting in its electromagnetic field, right, which has a certain amplitude f, right? So this sometimes people read this like a plus minus, but it's not a plus minus; it's an f, a capital F, right? It's the amplitude. That's just a charge, right, which we will set to equal to 1 later probably, or just absorb in some constant. That's the excursion of the electron with respect to the nucleus, right? And this is the only thing which counts in this excursion in the x direction. That's the only thing which counts if the electric field vector is pointing along the x direction. And k, which we will later not need, but just to fix the geometry of it, right? But this, as I said, is the classical and the energy of a classical dipole in a classical electromagnetic field. Now I translate this into quantized language, in this language of the operator sigma and sigma plus and A plus, which I had defined before, right? And so you translate, then, so you replace F cosine omega t. This becomes A plus A dagger. And these A and A dagger are the same A and A daggers which I had before, right? Which are the creation and annihilation operators of this quantized field mode. No. This thing is able of too many things. So okay, okay. Yeah, and I replace minus EX, right? I replace this by H bar G, and I will have to explain what lowercase g is, times sigma plus sigma plus. Yeah, and so now I have all these components. I have E minus EX, right? I have minus EX, which is this part and this part, right? And I have F cosine omega t, which is this part and this part, right? This now replaces my quantized language by these annihilation operators and creation operators of the electromagnetic field, and by the lowering and excitation operators of the atomic excitation, right? Remember that sigma acting on the excited state gives you the ground state, and sigma dagger acting on the ground state gives you the excited state. Right? So therefore now the total Hamiltonian of the atom driven by the quantized electromagnetic field, writes H equals H atom which was 1/2 omega sigma z, right? Plus H harmonic oscillator, which was H bar capital omega times A dagger A plus 1/2 identity, yeah, plus V. Yeah, and so now if we write it down in full glory, so we put in here the V as written here, right? And then rewritten in quantized language. So we put this in here. So we put the V in here in this explicit form in terms of these annihilation and creation operators on the atomic and on the field level, and then also make these explicit, so we get the following form. So equals um, 1/2 omega sigma z plus H bar omega A dagger A plus 1/2 identity plus H bar G A plus A dagger and sigma plus sigma dagger. Okay, well, I still owe you one thing, which is the definition of G. So this G here with G equals some constant where also the electric charge is absorbed times the matrix element between the ground state and the excited state. Yeah. So this is now the full Hamiltonian, which describes the energy of the atom, which can be either in the excited state or the ground state, which describes the energy of the quantized harmonic oscillator, which represents the field mode, and which describes the coupling between these two degrees of freedom, right? And now maybe let me see what we do now for today, to conclude for today. Yes, now we want to, as I said, right? So first, I mean, on one hand, we have the degree of freedom of the two-level system, which we want to move, right, in time. We want to imprint upon a non-trivial time evolution, as, for example, the Hadamard effect. Right? Then we have the free quantized electromagnetic fields, right? And V is the agent which covers these two degrees of freedom. So now we want to solve the time evolution equation, the Schrödinger equation, the time evolution Schrödinger equation for the atomic degree of freedom, so for the electronic degree of freedom, right? Under this coupling mediated by V, right? And we want to solve it in the easiest, how shall I say, reference system imaginable, right? So therefore, we will go now, we will write now down, or write Schrödinger equation down now in what's called the interaction picture. So we know what's the difference between the Schrödinger picture, the Heisenberg picture, and the interaction picture. These are different representations, right? So maybe just give you some idea, right? So and with this, then probably we'll conclude today. So now, let's say time evolution of a quantum system. So which is the governing equation? Which equation describes the time evolution of a quantum system? If it's unitary. Okay, good. Now, how does it? What's the can you tell me what I should write? Partial with respect to what? I mean, maybe, please, what's your name? Frank. So yes, now just shout at me, please, okay? Yes. I. D. Partial with respect to what? Time. Psi, right? Yeah. Equals. H bar squared. Ah, okay, okay. Yeah, but this now, okay, 2m, and then what? Huh? Laplace, just Laplace. P squared. So what is Laplace? Laplace is which Laplace is what differential expression? Second derivative, right? So it's the momentum squared, right? Okay, precisely, yeah. So, but where do I have I mean, I see where you want to go, but where is the momentum here? Did I define already a momentum of the particle? Oh, we don't have momentum. We don't have. So this is actually, I want it more general, right? So just the most general form without making, you see, without making the differential form of the Hamiltonian explicit, right? Because here in this quantized formalism, which I have with A dagger, right? I'm not, you know, let's say what you are after, you want to write down now already the Schrödinger equation position representation, right? Or in momentum representation, so in some space, in momentum space or in position space. Now I'm always writing down the Schrödinger equation just on vectors, right? Which are not yet given, where I do not yet choose the representation. So what you were after. Yes. 5 minutes. Yeah, I know. Okay, thank you. Don't worry. So let me see. Anyway, so now I just because I'm so bad in using this device here. So let's say I just want to write the equation like this: I h bar partial t acting upon a vector psi, right, equals h times psi. Yeah. And the total h, I had written it down above. Right, here's the total h, okay, right, which is composed of these different terms, right? But I'm not, let's say now, if I were to replace psi by x psi, which then often people write as psi of x, right? Then I would need your differential operator valued expression for the Hamiltonian, right? And then I would get maybe a Laplacian, right? But now here I don't get it because I do not choose yet a representation. I'm just remaining in the abstract vector space. Okay. So okay, and I was just told by the masters of ceremony that I'm running short of time. Don't worry. Yeah. So look, and now, so this is the time evolution equation, right? So now the time evolution, now h is given by h atomic plus h harmonic oscillator plus v. Now, however, I believe that I already know the atom very well. I know its eigenstates, right? I know its dynamics if it's alone, right? I know the unitary. I know what happens in time if I only have this guy. I also know what happens if I only have this guy. It's just a stupid quantized harmonic oscillator, right? So what I do want to know is I want to know how the dynamics of the isolated harmonic oscillator or of the isolated atom changes as I couple these two degrees of freedom by adding this additional v, right? So therefore, you can imagine that, let's say, I'm sitting on a what do we say, a merry-go-round, right? So I'm actually sitting in a merry-go-round. So this would be my unperturbed motion, right? So you can predict what will happen. And you wait another 5 minutes, and I will have done several times from this. The v now will somehow perturb me, right? It will push, right? And so therefore, what you essentially want to know is how the dynamics in the presence of v is different from the dynamics in the absence of v, right? And
the picture, the so-called formulation of the Schrödinger equation, which gives you directly access to this difference of the dynamics, which is only induced by V, okay, by V being non-trivial, is the interaction picture. So there's this here is the Schrödinger picture. And now we want to go to the interaction picture. Yeah. And now I give you some homework. I ask you to try to do the following, right? So now define psi with index I for interaction as e to the I h atom plus h harmonic oscillator times t over h bar times psi. Yeah, and find evolution equation for psi I. Have you done that already? Have you already seen it? That's a very important what you do. So you see, by essentially, originally you had I h bar dt psi equals h psi, h being composed of all these terms, right? And now I redefine psi I in terms of psi by multiplying it, right, with essentially the inverse time evolution operator generated only by the isolated atom and by the isolated harmonic oscillator, as if they were not coupled. So, and then I want to know what's the time evolution of this object under this Hamiltonian. I can tell you what comes out. What comes out and what you get, right, is I dt psi I equals Vi psi I with Vi equals e to the I h atom plus h o times over h bar times V times e to the minus I h. I mean, essentially here, this and this are the same, is equal, okay? So essentially, you get them in the interaction picture, as it's called, after this redefinition of your state vector, right? The dynamics is only generated by the coupling operator itself, which, however, has been transformed in this way. So it's essentially given by the original coupling operator, from left with e to the I h atom plus h coupling oscillator times t over h bar, and from the right with e to the minus I h atom plus h harmonic oscillator times t over h bar. Okay, and actually the relation is a little bit bulky, right? I mean, but you can see whether you can do it. Otherwise, please read it up until next time in the quantum mechanics textbook. It's in all textbooks, and it comes under. This is so to say. This is the. This is the Schrödinger equation in the interaction picture. Yeah, and that's important because it makes your life much easier. Because at the end, you do not need to carry along anymore the Hamiltonian of the unperturbed atom and of the unperturbed harmonic oscillator. Okay. Good people. So thanks for your patience and endurance. Then I think we meet again later in the week. question, they're going around all the time. And so I might also come tonight and see some of the other lecture. But if not, you write an email or so, or you try to reach me, right?
Yes. So your name is Julia.
No. The only So now what you actually do now, when you say inside I of T equal zero with T over 5, right? On the side of minus side plus side, right? Now we want to understand what happens now side I of T in general, then and E is not vanishing, so then you also get this plus E, right? But then of course this will not be true anymore, right? Right? So then the thing, so if you define CI, by acting upon this Hamiltonian, right, not compensate putting forward. Right? So therefore, we just again, we just like that. Now saying by the edge that plus E, right? Then by this is not here, right? So therefore you want to therefore you should write it. And then what science actually is relative. You can also imagine what is. Okay, that's your basic purpose. Now if you do a Schrödinger picture, you have your initial x in the right side of T. And it moves the state. Right? So this in the Schrödinger picture is the state. Now, of course, you can also say rather than state. What can also do basis states? The combination of this vector then us vector is vector also. So this we call also the active view, and this you consider as the passive. And now in this interaction picture, you essentially put all the time dependence induced by just encoding, right, on the coordinate system, right? And the time equation of the state is then generated by V on the yes. Oh, what would be V is just a meter, just N, right? So it's T versus interaction. Would be important for us, but it's very important. Yeah, the beginner, what size? So, very good. I think it's 1, 2, 3. I think this will be a volume. They don't need pressure. Yes, I try to do what I want to do. No, what has a problem? Right, so, I mean, the purpose of lecture is essentially to tell them how you physically do something. But they promise and this setup is terrible. Yeah, basically.
The microphone.
No, the microphone that we tune it down now. So we
okay,
tune it down
that's
so
good.
that here in the hall there is no microphone, so they hear better.
Okay.
Right.
Very good.
Still, we need it for the people offline, right, or online, right? But of course, this is not good because they cannot follow what you write down, right? Thank you anyway.
I would say I forgot my rectory. Something to show that maybe like this.
Okay. If you have it on Android, it should be seen.
If me, you are around. Yes. Are you around?
Yeah, that one, we used to push it.
But
Yeah,
you are
pen.
here. You are here.
Yeah, I'm around.
Because we can change the color. Yeah. This we can. This we can. Yeah, but this someone is outside.
So this for online.
Okay. Okay. Okay, so what we will do today is to have a deeper look in quantum algorithm. In particular, yesterday, we start to see how to exploit quantum parallelism in some way. We have defined a bitwise function, bit function. So let's say function which are going from 1 bit to 1 bit. So from 0, 1 to 0, 1. Bit too small. And we have seen that it's if we build something like that, so a unitary which is acting in this way, that x, y is giving under unitary transformation to x, y plus f of x. This is a good unitary, and it can be therefore implemented to a quantum computer. Okay, of course, depends on your function, and the circuit will change. Okay, I just want to focus on this. So, why, in your opinion, we are not using, for instance, this one, like x, x, y. With the Why not this one? What do you think about that? You have also to ask yourself why you do in a way and not in another way. Any idea? Any guess? Shall we write the table of truth and see if we get inspired by that? So if we write the table of truth, this is 0, 0, this is 0, 1, 1, 0, 1, 1. And then here we have 0, f of 0. And then here we have 0, f of 0, f of 1, sorry. No, f of 0, sorry, because this is f of x. And here we have 1, f of 0. And here we have 1, sorry, f of 1. Okay, you are not sleeping. Very good. That was just to be sure that you are awake. And then you have 0, f of 0, and 0, f of 0 negation. Okay, let's call it like that because the negation, this is the negation. Okay, because y is 1, and then you have 1 f of 1 and 1 f of 1 negation. Okay, now you can answer to my question. So why we are using second and not first? Every time I asked you why gate is not working, the answer is always the same. Is unitary? Yes, no. Why? Can you recognize just by looking at that?
This one. Can you come back? You cannot come back. So it's not invertible, right? Because these are the same. These are equal. So you cannot, every gate that you create has to be invertible. Okay? So if two inputs give the same, exactly the same result, that means it's not invertible. So this is a very easy way to look at that. And if you do like that, these are different and these are different as well. Doesn't matter how much is f of 0, but this is the negation of f of 0. How much is f of 1? I don't care, this is the negation of f of 1, and they are all different. Okay? So you can build, so basically we have used the y plus, we need to mix in some way. In output, the input, otherwise, I mean, the second qubit input, otherwise we don't get a good gate. Okay. Okay, of course, bit function can be generalized to any bit. So if I have f of x, where x is the arbitrary number of qubits, we have a function that is going from 0, 1 to the n to 0, 1. Okay, like a bit function of many variables, many bit variables. So one output, many input. This is very general because bit by bit you can build any function you like. Anything you can imagine can be built bit by bit. Okay, so if you write any bit function, if you write a bit function, you can write any function. Okay, of course, I mean, this f is, there are many functions that are defined on, for instance, 1 bit for different functions, you can define it. And of course, there are many more possibilities of defining the function. You have 2 to the n function, different function that you can define on n bits. Okay. Okay. Okay, let's now have a look to an interesting properties of this circuit here. So now our goal is to understand how it's possible to have some computational achievement from this kind of play that we played yesterday. Okay. So you have, for instance, this circuit here, which is 0, and then Hadamard's, and then 0. And then I don't care how I will build this function, but it's anyway a unitary, right? So it's a unitary. This is a kind of gate. This, I don't know, it depends on the function. And the input is x and y, and the output is x and y plus f of x. Okay, I will just call unitary f, because this is a unitary that it depends on the function, the kind of function I define. In this case, it's just a bitwise function, but if in input you have more than one, if x is a list of qubits, then this would be bigger unitary, but it's anyway a unitary. So as output, the wave function is, of course, as we said, x and yes, okay. This we already said. Let's say it's already written here. I don't write here because otherwise it can be confusing. Okay, what is psi? Well, psi, so the wave function that exits from here
you see that here there is a superposition of 0 and 1. So the output would be 0, and the y is 0. So the output would be 0 and f of 0. Okay. Plus 1 and f of 1 divided square root of 2. So this is the wave function as output. Sorry? What f is? This is only f. Yes, sorry. Yeah, this is the output. So it's the wave function as output. Okay? It's the output wave function. So the output wave function is made by 2 qubits. This is the first qubit, and it's, of course, a linear combination of bases. Yes. Okay, sorry. Okay, so what is interesting in this writing is that phi is a single unit vector, so it's a single, in some way, result. We have applied some rotation, and what did we have an output? An output, we have something which is, let's say, a single circuit can be used to evaluate the same function both on 0 and 1. Okay, so this is interesting because one single circuit in one shot I apply and I got in output something which is calculated with function both on 0 and 1. This is what emerged yesterday, no? Can I actually calculate the function on all the phase space, all my qubit space? Yes. In output, you have a wave function, we have many terms, and many terms in some way contains information about f of 0 and f of 1. So only where, okay, some information about that. This is nice in principle. It's not particularly useful. Why is not particularly useful? Because then if you go to measure this, you will have only one of the two. Okay, so even if the wave function potentially contains the function calculated in both 0 and 1, so in parallel, but then when you go to measure, only one of these outcomes will be known to you. So we are going on the right way, but let's do something more. Because we would like to collect this information, not in two different states, but only in one state. That would be great. So if we are able to collect this information about the evaluation of the function on a single qubit or on some qubits. Is it clear? Okay. So how do we do that? First, we have to generalize this circuit. To generalize this circuit, we have to generalize the Hadamard gate. And the Hadamard gate for n qubit, if I have n qubits, if I have n qubits, then you can define this operator here, okay, which is, let's say, Hadamard repeated many times, okay, for each qubit. So this is equivalent to Hadamard, okay, and so on, n times. If I have something like that, I would generate in output all the possibilities of bit string of the 2 to the n bit string. Okay? because every bit has both, is split in 0 plus 1, and then of course these are combined in the meaning of the tensor product, so exponentially large, and so we will obtain that. How can we? And here we have, of course, 0, 0, 0, 0, and so on. Okay, so we can say that when we apply Hadamard to the n, to 0 to the n, okay, so to many qubits, we obtain all the combination. How can we write all this combination in a compact way? We will use this this formula here. We will just say the sum of x, where x is a vector, where you have x1, x2, which is composed by many bit variables, and each bit variables, of course, is a bit variable. So it's going from 0 and 1. Okay, how many do you have of them? 2 to the n. So 1 over square root of 2 to the n is necessary. And here we have just x. Okay, where x is the bit string. Is that clear, this notation? So x is the bit string. So x one time is 0, 0, 0, 1, 1. No, not of course. 1, 1, 0. Another time is, of course, depends on the dimensionality. And another time is another. Okay, 0, 0, 0, 0, 0, 1, and so on. So you have a so-called perfect, I mean, a perfectly distributed, equally distributed vector in all the phase space. You are visiting everything in the phase space. Okay. Okay. Okay, we can continue. Then if we build this with what we said before, so you have n qubits, so you have something like, we will build the following circuits to the n, and then you have Hadamard to the n, which is bigger in some way. So here I just, and here you have the other one. Why it's separated? Because it's a kind of ancillary qubit, which is necessary to evaluate the function. Without this, you cannot have, because it will not be invertible. Okay. Okay, so this is great because this will produce what? Will produce a state psi, which is 1 over square root of 2 to the n, the sum over x of x multiply f of x. So in some way, you have in output a bit string and all the possible combinations. So you have a bit string and the valuation of x on that bit string. Another bit string and the valuation of x on that bit string, and so on. Okay, so you have actually, you did calculate effectively the function on all possible states, exponential number of states. Okay, so this was a kind of discussion we had yesterday. So then what is the point? Is that, yeah, you have this magic 2 to the n wave function, but then at the end you have to do a measurement if you want to know something about that. And when you do a measure, you just have one possibility back, not all the possibility back. Okay? Okay, very good. Okay. So can we do better? Of course, we can do better. We can do better. I will show you one case where we can do better. We can do better using this circuit here. So to exploit this capability of quantum parallelism, we have to use other properties of quantum system. We have to use interference. So we would like that all these exponentially large number of small pieces that are all around the phase space interfere with each other in order to let the information to be squeezed in some way in some qubits, not just spread around. Okay. So for instance, this is done through a circuit like that. I will show you a circuit, a very simple circuit, and then we will build another circuit which will solve a problem that in principle classically is exponentially difficult, but with quantum computer it can be very easy to solve. Okay? It would be not useful problem, but would be just some example. Okay, so don't be worried if what we are doing is you don't see the utility sometimes. Of course, you don't see the utility. We will you will see some application in quantum chemistry. You may probably someone else give some perspective, I guess, on the utility, probably, maybe not. Yes, please.
My question is, you mentioned something about how that we don't want the data to be like spread over, but we are compressing it into some qubits.
Yeah.
So can we say that what we have here is like we are encoding data within a quantum segment? Are we encoding information?
It's not really encoding information because we are really changing also our information in some way. It's an elaboration of what is happening on a quantum computer in order to put our information just in a smaller amount of qubits. Maybe it will be clear when I show, when I show what's happening. And also, which is a stupid problem that we will go to solve. Okay, so no, it's not yet related to cryptography up to now. Otherwise, it would have been useful. Okay, so this is just this is a very simple circuit. This you have H is basically the same circuit as before, but we just added another Hadamard. And we started from 1 instead of 0. X, Y, X. X, this is intended as a vector. Okay, this is to the n. Okay, very often this is actually omitted, and we just talk about 0. And many books do like that. I don't like very much, but of course the notation is that. So the first n qubits are the first zero, and then all the others are the last. All the other is just one. Okay, and then you have, so not all the other, but just the other. F of x, so this is unitary. Then we apply the Hadamard, and we will do something like that. Okay, so f is a general function, a bitwise function, so it's going from 0, 1 to 0, 1. Very good. Then you have, we will do what we are using, what usually we'll do. So we start from a wave function psi 0 here, and then psi 1 here, and then psi 2 here, and then psi 3 here. Okay, this is always the full wave function, so it's referring to all the states. Okay. Okay. We can do the algebra now. Just remember, what is doing Hadamard on 1 is giving the 0 minus 1. Okay. So psi 1 would be just this one. Sorry. So psi 1 is 0 plus 1, and then 0 minus 1. Okay, this is easy. This is, of course, always in some way. Okay, no, this is not yet to the end. Okay, forget this. We work only on 2 qubits because it's simpler. Okay, just 2 qubits. It's not yet. It's next time we will go on a bigger system. Otherwise, we cannot see the advantage. Okay, let's first see how UF act on X and Hadamard 1, which is this one. Okay, this is X and Hadamard 1. So if you have X, so it will produce X and 0 minus 1 square root of 2, and after UF you have X, and then you have 0 minus 1 square root of 2 if f of x is equal to 0, or you have minus x 0 minus 1 square root of 2 if f of x is equal to 1. So depending if f of x is 0, 1, you will have one case or the other case. So I can use a notation that includes both cases, just writing minus 1. Oops. So both cases are included in the notation minus 1 to the f of x x, and then you have 0 minus 1. Okay, square root of 2. Okay, and this is only how UF act on this. But actually, you don't have this. You have here. You have, instead of x, you have. If you look before, instead of x, you have this one. Okay, so you have this. So we have to extend this to the Hadamard x, Hadamard 0, which is the equally probable superposition. And if you want to do that, you will have that psi1 finally is equal to -1 to the, I'm just applying 2 times what I wrote before, one for 0 and the other for 1, plus -1 to the f of x, 1. Then you have square root of 2, and then you have the second qubit, which is unchanged. Sorry. There is not way to. No. Ah, yes, I can come back. Okay, and then 0 minus 1. Okay. This is actually not psi1, sorry, so this is psi2. Okay, I can write in a different way this psi2 because I have to explicit in some way this function. Otherwise, I don't know which is the sign of this linear combination. So how can I do that? I can do in this way. So psi2 is equal to, so you have two different cases, either f of x and, sorry, this is f of 1. This is f of 1, okay? Okay. So either f of 1 is equal to f of 0. In this case, you have plus, but this depends, because if f of 0 is equal to f of 1, then you have plus or minus you have you have 0 plus 1 divided by square root of 2, and then you have 0 minus 1 divided by square root of 2. Or you have f of 0 different with respect to f of 1. And in this case, you have 0 minus 1 divided by square root of 2. And 0 minus 1 divided by square root of 2. So this plus or minus is, you have plus if f of 0 is equal to 0, and minus is f of 0 is equal to 1. Okay, of course, this depends on f of 0. And then you can apply the Hadamard gate. So you can do one step further and apply the Hadamard gate, and you get with psi3. When you apply the Hadamard gate, you apply on the first qubit, as indicates the circuit. And the Hadamard gate is nice because when applied to this, it's back to 0, and when applied to that, it's back to 1. Okay? So when you apply the Hadamard gate, you have something like that. You have plus or minus 0, because Hadamard gate applied to before is 0, and then you have 0 minus 1 if f of 0 is equal to f of 1. And then you have plus or minus 1. Then you have 0 minus 1 if f of 0 is different between f of 1. Okay. How can we write in a different way all this stuff in a compact way? We can write like that. So we can write in this way. So if we have f of 0, if we write f of 0 plus f of 1, what is the result? This result is giving the 0 if f of 0 is equal to f of 1. Okay, and is equal to 1 if f of 0 is different with respect to f of 1. So writing in this way, it allows us to get rid of, I mean, instead of having this definition on the side, we can put in some way this definition in the first qubit as writing in the same qubit, in the first qubit. Because the first qubit, it depends if it's the first case or it's the second case. So you can finally write psi3 in this compact way. Psi3 is equal to plus or minus f of 0 plus f of 1 and then you have 0 minus 1. So this is the first qubit, this is the second qubit. So what we obtain now. What's happening if we measure the first qubit? If we measure the first qubit, if we measure the first qubit, if we get a global property of the function, so we will get the sum of the function calculated in 0 plus the sum of the function calculated in 1. So in some way, in the same qubit, in the first qubit, are contained the information both of the function calculated in 0 and 1. Okay, it doesn't matter the sign, I mean. But if the first qubit is 1, it means that the sum of f calculated in 0 and 1 is 1. Minus 1. So let's compare this writing with respect to the other writing. The writing that we had before, that we say, okay, we can evaluate in parallel stuff. I can write this here. So before we have what is that we have before? We have the same, yes, we had this one before. Okay, before. Because we have a wave function that was 0, f of 0 plus 1 f of 1. Okay. So these two writing up really different. Why they are different? Okay, first because this has two terms. This is only one term. Okay. Very good. One term. So if I measure the first qubit, I just obtain a result. If I measure here the second qubit, I got something, sometimes I got f of 0, sometimes I got f of 1. I'm not sorry, it's actually it's not parallel in this. Okay. I'm not evaluating the function on different ways. Here, if I just measure the first qubit, I know a global property of the function. So the sum of the function on all the bases, both on 0 and 1. Okay, you know what I mean? You get the point. So this is very nice because the information of f of 0 or 1 is only in one piece, one term of the wave function. Okay. I don't have many terms as here. Yeah, I have two terms. Okay, but you can imagine that all these terms can be very large. Here I have the information, the wave function is made only on one term, and this term contains information of both f of 0 and f of 1 at the same time. Okay, now we will see the generalization of what we have done, which is called, what should I say? So also we have seen another different characteristics of quantum computers. So in quantum computer, you have to use some interference to move the information wherever you want and to get the answer inside your circuit in some way, in a clear way, and to expose directly the answer. Okay. So we are going to have a look to this Deutsch-Jozsa algorithm. And this will answer the following problem. As I say, this is a stupid problem, so it's not useful. Okay, but we can prove that quantum computer may have some advantage. Okay, so what is the problem? It's always a problem of Alice and Bob. Alice select a number. This number is a bit string, basically. So we call this number x. It's a number between 0 and 2 to the n minus 1. Okay, where n is the number of qubits. And send this number by email to Bob. Okay, suppose, I don't know, whatever, n equals 10, so from 0 to 1000, and send this number to Bob. Bob has a function f on this bit string, and this function can be evaluated of the number of Alice. This function has the following characteristic. This f of x can be of two different kinds, or either constant for every bit string, or balanced. What it means balanced, that f of x is equal to 1 on half numbers, and is equal to 0 to the other half of numbers. Okay. So it's just a bit function that it depends on the input.
can give either the same number as output or can be a balanced number. That means that half of the input gives 0 and half of the input gives 1. Okay, so how many numbers has to send Alice to Bob to be really sure if the Bob's function is constant or balanced? So Alex has selected a number between 0 and 2 to the n, okay, and send it to Bob. Bob has a function that can be of 2 different kinds. Alice doesn't know the function that has been chosen by Bob, but she knows that Bob has only 2 possibilities: to have a constant function or a balanced function. Okay, only one of the 2. So the question is, how many and then what is doing Bob is evaluating this function and give back the result to Alice. So for instance, Alice is sending 0, 1, 0, 0, 1. Okay, Bob is telling, okay, the function evaluated on this string is 0. Then Alice is sending another number, and Bob is telling, okay, the function evaluated on this is 0 again. And it's repeating like that. Okay, of course, if at a certain point it say it's 1, then Alice is sure that it's not a constant, but it's a balanced. But the question is, how many times you have to send the email to be really sure that the function is either constant or balanced? If the total number are 2 to the n, sorry? So Alice has to send a bit string, so a number from 0 to 2 to the n times 1. That means a bit string. Okay, binary. And then Bob evaluates this number with this unknown function and they give back the result to Alice. Suppose that Bob give back the result. The first result on the first number invented by Alice is 0. The second answer is still 0. The third answer is still 0. So Alice doesn't know yet if the function is constant or balanced. Because to be sure that it's balanced, you have to evaluate half numbers. You may be very unlucky and you send half numbers minus half. If you send half numbers and you send exactly the half number that Bob have chosen in the balance function, the answer would be constant even if the function is balanced. Is it clear? No. So you have a function that can be either constant so you have this bit string 0, 0, 0. Okay, let's make a simple case. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, no, 0, 1, 0, 0, 1, 0, 1, and so on. Okay. So 1, 1, 0, 1, 1, 1. Okay, let's suppose that
And then the function, and let's suppose that Bob is writing a function which is balanced. This balanced function gives 0 to this number, 0 to this number, maybe 0 to the odd numbers and 1 to the even numbers. Okay, this is balanced. And then Alice has to guess if the function invented by Bob is balanced or constant. But maybe Alice is giving to Bob all even numbers because she's unlucky. I don't know. Okay. So it has to send to Bob how many questions to understand that it's actually balanced and not constant. Was the Alice is sending only this, get always 0. And then it's sending one more and get 1. But if she wants to be 100% sure that of the nature of the function, she needs to send half plus 1 messages to Bob. Okay, half plus 1. Half plus 1 is 2 to the n divided by 2 plus 1. Because the numbers are 2 to the n and half is half. So it has to send 2 to the n minus 1 plus 1. Okay. This is only one kind of function that invented Bob, which is in agreement to the game of choosing a function that is either balanced or constant. But Bob might have chosen other function. Okay. Suppose that Bob choose this function 1, 1, 1, 1, 1, 1, 1, 1. Okay. Alice is sending 4 questions, 4 ones back, but she cannot be really sure still after 4 ones that this is constant. Okay. Because, for instance, before this sequence gave 4 1 answer, but actually the function was balanced. Is it clear now? A bit, yeah, I think it's clear. Okay, so the question is, the point is that to solve this problem, to understanding the function, Alice had to set to Bob an exponentially large quantity of because 2 to the n minus 1 is exponentially large with respect to the number of digits. It's a lot of effort. Okay. But Ellie is much smarter than Bob. So what is proposing Alice is, well, Bob, could you build a unitary transformation UF on your quantum computer to evaluate your function on n qubits? So could you build a circuit that evaluates your bit function? Okay. Well, and then Alice is sending one quantum state to Bob. The quantum state that is sending Bob has n plus 1 qubit. So Alice is sending this. Bob is building this. So this is Bob's job. So to build okay. to build this, and this is the Alice job, to send n+1 qubits to Bob, and then is asking to calculate this function on the state that give that Alice provided, and give the answer, which is a bit string, to Alice. And Alice now known with only one measurement of quantum computers if the function is balanced or not, or is constant. Okay, it sounds a bit mysterious now, but now we will see how this is working from the point of view of Alice. Okay, which kind of what Alice is doing. Okay, so Alice so if Alice is able to evaluate something on the strange oracle function, they are called oracles, this function. Okay, the strange oracle functions on a state that she decides, the quantum computer can actually solve the problem in just one step. And understanding if the function is balanced or constant without doing 2 to the n repetition. How to do that? We will do it. We will figure it. Okay, so this is the circuit that has to be built. Okay, now remember last time, we say how is teleportation, and now we are drawing the circuit that solved the problem that we said before. So here you have 0 to the n state. We have Hadamard, the n. Then we have the unitary that Bob built. Of course, Bob needs also an ancillary qubit that is provided by Alice. So this you have X, you have Y, you have X, and you have Y plus f of X. Of course, this X now is a bit string. And then you have H to the n again. So what we are doing now is since we have seen that this kind of mixing Hadamard 1 and Hadamard 0 is doing some interference such that a lot of information comes on the first qubit. Okay, we have seen it before. We will try to do the same and see what happens. But we are doing for all qubits. Okay, so this is side 0. This is psi 1. Of course, this is going over through the states, all the states, psi 2, and then this is psi 3. Okay, and then we are doing the same calculation as before. Let's have the same calculation as before. So psi 0 is just 0 to the n. I will probably drop this notation because, as I say, sometimes you just write 0 even if there are many. Okay. So psi 1 we know before how to treat it. This is the sum over all the bit string. So x belongs to 0, 1 to the n to x. So this is the uniform superposition. And this is the Hadamard applied to 1. in the ancilla current. Okay. Okay. So I now writing f of x, where x is this bit string. So this means f of x1, x2, x3, and so on. So this is a function of many variables. It's a bit function of many bit variables. It's going from 0 to the n to 0, 1. Okay, which is exactly the function that is built by Bob. Function that is telling if one number is you give one number in bit string and you have an answer, 0 or 1. You can also see this function as, oh, there are many of these functions, also data science. Okay, so what's happening now is that we can have one, we can make one more step. So first we see side 2. After, what's happened after evaluating side 2? This is just the sum over x, and then it's -1 to the f of x times x over square root of 2 to the n. And this is 0 minus 1. So this is after evaluating this. After that, I have to apply again Hadamard. Okay, this Hadamard here, the last one. I have to apply the Hadamard to the first n qubits. So let's write in a compact way as the Hadamard acts on 1 qubit. So how this Hadamard apply to 1 qubit? We know how Hadamard acts on 1 qubit, of course, but I want to write in a different way because now we have many qubits and we have to use a smart notation, otherwise we get lost. You said I'm already lost. So this is, we can see like that, 0 plus -1 to the xi. Okay, in this way, if the state is 0, we have the superposition with plus. If the state is 1, we have the superposition with minus. And square root of 2. Okay, I put square root of 2 on the left, so I don't have to write anything. Okay, I can write this in another way. I can write this in this way, which is more convenient when you have many variables. So sum of zi that belongs to 0, 1 to -1 zi multiplied by xi. And then you have zi. Okay, it's just the same. It's only a matter of rewriting this. So this qubit here can be 0 on 1. And according to z, if it's 0, 1, you might have the first term or the second term. Okay, so now we are ready to really to work with all the qubits. So to apply Hadamard to the end, apply Hadamard to the n on x1, x2, on x, okay? xn. And this would be just the sum over z1, z2, z3, and so on. Every z belongs to 0, 1. Minus 1 to x1, z1, plus x2, z2, plus, can I move it? Yes. Plus x3, z3, and so on. Okay, and this is applied to z1, z2, z3. So this is just a generalization of what we have. We're almost there, because we're almost there. I just write again here. So h to the n apply to x. And why it's sometimes it's not working. Apply to x. Okay. Then is okay. How can we write this? This looks like a scalar product. So we can just write this as a sum over 2 to the n over the sum over all bit string z. Okay, it's like it was a vector. I don't write it as a vector because before I didn't write it as a vector. So I don't write the arrow on the top. And minus 1 and x scalar z. And this is another bit string. So x scalar z is kind of inner product modulus 2. Okay. Okay, so but now so far we have done only this. But our wave function psi2 has also, where is psi2? Yeah, you have also f of x. Okay, so it's very similar, but you have f of x. So you don't have only x, but you have another sum over all the possible bit string. This was just on x bit string, a general bit string. So psi3 is the sum over z, the sum over x minus 1, and then you have x times z plus f of x, z. And then you have 2 to the n, because you have 2 times square root of 2 to the n. And then you have 0 minus 1. Okay, so finally we have sum. Now the sum is of many terms. Okay, very many terms, and but in the sum there is this scalar product, and then there is also the sum of the evaluation of f of x. Okay, so to understand what is going on, we would like just to calculate the amplitude of the first qubit. Sorry, of the first qubit. The amplitude of one state among all these states. These are many states. Okay, so superposition of everything, so you have all possible states. So among all these possible states, we choose one state and we calculated the amplitude. So we just choose a state, this state here. Sorry. This state here. 0. Okay. So how is evaluated this function on the 0 state? I mean, what about this? I only consider the 0 state. This is sum of z of all the states. So when z is all 0, what's happening? So if z is all 0, then the scalar product is 0, and then psi 3 is just equal to not psi 3, but because we don't want psi 3, but the coefficient. Let's write it like that. Not really psi 3, but the coefficient. So the coefficient of this 0 state is obtained when I put here 0 only. Okay, so I have the sum over z. I don't have anymore because it's just 1. I have the sum over x, and I have -1. This is 0 because z is 0. So is -1 to the f of x times 1 over 2 to the n. Okay, so this is the coefficient of the 0, 0, 0, 0, 0, 0. How much is it, this coefficient? Well, it depends on the function. If f is constant, how much is the coefficient? The sum is over 2 to the n. Possibility. Okay. So if f is, yeah, it depends a bit if f is 0. Suppose that f is constant and it is 0, and then you have 2 to the n terms, and here you have 1 over 2 to the n. So the result, the amplitude is 2 to the n divided by 2 to the n. Okay? This is 1. If f is 1, it can be a different sign. I don't think so, because 2 to the n is always odd, so it should be also 1. So what is happening here is that in one coefficient only of the many qubit representation, you have incorporated the sum of an exponential evaluation of the wave function. Only one coefficient. Okay. Then, because of the nature of the function can be constant, this gives exactly 1. if is constant. If it is, what's happening if, yeah, let's do it like that. What's happening if f is balanced? Well, if f is balanced, in this sum, half of the function would be with the minus sign, half of the terms would be with minus sign, and the other half of the terms would be with plus sign. Okay, so they cancel out, and the result would be 0. So the coefficient of the, let's write with, of the 0.000000000 qubit is either 1 or 0. And I made a measurement. If it's 1, this coefficient, it means that this qubit is the only one. The state is just this. Okay, because the normalization, if one coefficient is 1, all the other has to be 0. Okay. So it's enough to see, to measure, to make one measurement, and to see if I get a 000 string, it means that I am in this case. If I get any other string, I am in a balanced case. Okay. So in some way, this is okay. It's a kind of toy model. It's not very useful. Small application for that, but it's just to show one simple example where you can actually have a quantum computer which is doing one single evaluation, okay, and solve a problem that in the classical way, you have to make an exponential number of evaluation of email, trial to understand if a function is actually balanced or constant. Okay. How did we do that? We use this kind of interference between the qubits with an equal superposition with the plus sign, and qubit with the equal superposition with the minus sign. We played on the sign of the. We use a kind of interference on that. Okay. Okay, of course, there are more useful problems to solve. I think that we will see with Divya, maybe tomorrow or the day after tomorrow, I don't know. You will see, for instance, one application of the quantum Fourier transform, which is applied to find the energy of the quantum state. You can find quantum Fourier transform. You can make Fourier transform in on quantum computing and having much faster than on classical computers. And for this algorithm, this is something I have to say. I want to show you a bit another algorithm, but before I just ask if you have questions. Question? Another question? I know that the algebra you get lost. Sure. I will forget lost. You received the lecture notes from yesterday? From Harry Martin? No, by email? No one did? No lecture notes from yesterday? No. Okay.
email from that. Go to Gary. Send me the letter. Because he told me yesterday, you should send me the next note. Because he didn't ask me. I mean, not the lecture note, the notes. This note, yeah, this note. I'm also preparing some lecture notes. So we do better with some text. Not yet finished, but that's a minor definition. I'm there together with the band. Did you receive anything? Okay, so.
It's any,
He sent something.
Okay. So let's see another algorithm which is not very, I mean, that it has some quantum advantage. Not big quantum advantage, I have to say, but at least it's useful algorithm. Okay. At least you see something useful. We will not have time to do all the derivation, but I want to show this algorithm also because it changed the way you think about algorithm. You always think about algorithm as something that, okay, you are, I mean, yeah, you follow something and you follow a certain procedure and you have a result. But this is a bit different in concept. So this is the algorithm for quantum search. So it's the Grover. Algorithm for quantum search. So what I will do now is that I will explain you some part of the algorithm. Probably I will not be able to do all the algebra, but then at the end I will show you implicitly what's happening. Okay. Okay. The problem is the following. The problem of search. So suppose that you have a certain number of records that satisfy a condition criteria, like I would find on all the book which has this author in a library. Okay, or I want all the book that has this title. If the book are distributed randomly, how is the expected time to find the book? Right? Yeah, I mean, the book are randomly displayed. Okay, so what can you do if you have to look for a book and you don't know the color of the cover? You have to open one. Okay, so on average, you will take you will revise half of the book. If you are lucky, it's the first one you check. If you are unlucky, it's the last one. But on average, would be something which is proportional order of the number of the book. No, you know this. This means that this is going as the time is scaling linearly with the size of the library. Well, the quantum algorithm promises that you can find the book with this scaling. Okay. Well, this scaling is not exceptional. I mean, we don't want to build a quantum computer to just have a scaling which is square. We want to build a quantum computer to tackle scaling that are exponentially into linear or exponentially into polynomial and be complete problem into polynomial problems. But anyway, this can be interesting. Okay, so let's just concentrate on the index of the element, or on let's say on the numbering of the book. And suppose we are looking for a certain index. Okay, book number 355, but the books are not sorted in any way. Okay. So the number of the book n, suppose that this can be written as power of 2. So the index is stored into n qubits. And then we can build a function. So we have a bit string and a function x. If a function which is acting on the bit string, s is always a bit string. Okay, so x is 0, 1, okay, to the n is a bit string, and this function is equal to 1 if the book match, or if x is solution to the search problem, and if equal to 1, sorry, and if f of x is equal to 0, if not solution. As here we have same problem as before. We have to evaluate the function, and the function is answering the problem. That is all the editor of this book matching with what we want. Yes. Actually, this is working also when you have, yeah, like in an answer, you might have more than one book that is matching this requirement. Okay, it's working anyway. But we can, just for simplicity, to so of course, if you want to use a quantum computer, you have to implement this function, of course, in a quantum system. Otherwise, you cannot do it. So you have to create an oracle, which is doing like that. So the oracle needs an additional qubit. So this is as usual. And so you have x, this is x, yeah, this is x, which is already, we have already seen that it's n qubits, let's say. So, and this should be something like, so after the oracle is applied, you have x and q plus f of x. So also here you have a very good, if you enter, for instance, the equally weighted superposition state, you at the end you have all your bit string, and the last bit is saying if the book is matching or not, 0 or 1. But the problem is always the same. The problem is that this is not happening to you, because when you have a measurement, only one of that is, if you're lucky, you match, you take the one which has 1 in the last qubit, so that means it's matched you. But if you're not lucky, it's not working. Okay. So also in this case, it's more useful to apply the oracle when Q is in the state 1 square root of 2, 0 minus 1. Okay, so what's happening if you apply the oracle to this state? If you apply the oracle to this state, it's happening the following. Sorry, this is 0. This is 0. 0 minus 1 over square root of 2. If I apply the oracle, it's happening that if x a solution, x a solution, then the oracle is transforming this in x, and you have 0 minus 1. X not solution. The oracle is transforming, this is minus x, 0 minus 1. You can, with the very little algebra, you can see that. So basically, instead of being, what is doing the oracle on this state, with this state as input, is not giving as answer 0, 1, but it's just changing the sign if it's a solution or not. So if it's a solution, the sign of the string remains the same. If it's not a solution, the sign of the string is changed. Okay. This depends on the ancilla qubit. The ancilla qubit is this one. This is actually how it's acting the oracle. So you can imagine that you have this oracle. In input, you have many inputs. And then the oracle will change the sign only of the, actually, let's say, we will change the sign of the books that are not solution. Yeah, sorry, it's the other way around. Yeah, that's what I was saying. I got just confused. So if it's not solution, it's not changing the sign. If it's solution, it's changing the sign. So in some way, it's pinpointing which is the solution, and the solution is kind of marked with the sign. Okay, just remember that there is, of course, there is a big difference between knowing a solution, which is quite difficult, and just checking if the solution is good or not. Checking, usually, it's much easier. Knowing the solution and finding the solution is much hard. So, okay, I will just write a global way. So this is the oracle. So the oracle is just changing the sign. So you have the scheme of the. Let's say that the scheme of the algorithm is the following. You have an equal superposition state. Equal superposition state. Okay. You know what is an equal superposition state? Just Hadamard applied to 0. All Hadamard applied to 0. So you have all the states possible. Then you have this oracle, and the oracle mark the solution with the face, marking solution with the phase. Okay. We have seen how to do it. So this, so far, you know how to do it. Because it's just making a normal oracle with this 0 minus 1 instead of 0 as ancilla qubit in input. Okay, and then you have another step. And the other step is called diffusion step. What is doing the diffusion step? It's another unitary transformation. This unitary transformation, but it takes quite a lot of time to understand it, I think. So we cannot do now. It's called a diffusion. What the diffusion step is doing is amplify the amplitude if negative, let's say. What this means? Okay, the oracle is just saying, okay, the solution has minus sign, and then there is this other gate that you can write. I will send you the. Maybe I can send you the. I can write here. Okay, I can send you all the stuff also written by hand. Just finish this, and then the LaTeX will come in a couple of days. So this diffusion amplifies the amplitude only if negative. So here you have the equal superposition state. The equal superposition state is has all the amplitudes positive. Okay, all the amplitudes are positive. Then you mark the solution with a minus, and you find a way to have a gate that amplifies the amplitude only if it's negative. Okay, so this amplification of an amplitude is negative. It's getting more negative. Okay, that is also doing something else. But in some way, every time you apply this, what you have marked before, it's amplified in amplitude. So the amplitude of the matching terms is getting bigger and bigger. What is the amplitude? It's the coefficient in front of the full superposition. So that means that they are becoming more and more probable to exit as a result when you do a measurement. Okay. And then you repeat several times. You repeat this several times in order that every time the amplitude of the solution gets bigger and bigger and bigger. Okay. And it can be calculated, it can be seen that if you repeat this a number of times, which is proportional to the square root n of the qubits, then the amplitude of the solution becomes dominant. Basically, become the only one. It becomes bigger and bigger and bigger, and it's close to 1. So what you're doing after square root of n of application is just to make a measurement, and you will only measure the solution. Okay, I can show this with the picture. I like to have. It's possible to connect the computer. Yes, I have just to. Maybe yes. I have just to connect with the with Zoom. So you see that this. I just need the Zoom code. Thank you. But maybe. This is the Zoom code. The password of the Zoom. Yes. It's here. Okay. Yeah. Okay. Okay. Sure. Let me just mention it from my phone. Meeting ID. Meeting ID, I know. I know the meeting ID. Okay. The passcode. Yes. 7571. 757162. Can you share? So you want to share? So let me stop sharing. Because yeah. So what I like to do several times, very often for outreach presentation, is to show on real cases how quantum mechanics can work. So what happens if you use quantum object and we can actually work on books as we can work with quantum mechanics. Tomorrow I will show you another example of something that looks. It's a physical object that it's behaved like a quantum mechanical object. So the problem is that my PhD student and I went to the university library to borrow a favorite book. This is, of course, Modern Quantum Chemistry. So the problem is that when we arrived, we found, shelf. This is the non-digital way of categorizing book that was some time ago the only way to have categories. So you have here inside this many cards, and every card contains the name of the book and also the place where to find the book, title and everything. Okay, if they are in alphabetic order, it's very easy to find a book. If they are mixed, it's not. So the cards are now on the floor. So what should I do? And the librarian said that the only way is just to take one by one the card and check it. Okay, how much time it will take? You need 10 seconds because it takes some time to take it and read it. I have to use my glasses and so on. So it will take about 14 hours to find the book. If I'm lucky, 0, if I'm unlucky, 28 hours. Okay, but I always bring my quantum computer with myself. Okay, always my backpack. Yeah, this is me when I have short ears some time ago. This is an IBM quantum computer. It's not IBM quantum computer because it's just a skeleton on the IBM quantum computer when I was visiting IBM some years ago. Sorry. So I wanted to say, okay, but I have a quantum computer, so I can use the Grover algorithm. How this Grover algorithm works on this paper paper cards. Okay. So it works in this way. You have a big bag, and you put all the cards in the big bag. All the cards are passed through quantum computers. When in the quantum computers, the Grover algorithm work on this card. How is working on this card? You know now how it's working on this card. It's amplified every iteration, the probability of finding that card that I know. Okay, because I programmed the function in the quantum computer, they recognize the ID of the number I'm searching for. So that means that every time, and how you can represent this in a physical way. You can represent, for instance, that the cards of the that are matching the book are replicated. Every time the cards that are matching the book become the double. Okay, it's a kind of way to imagine how the Grover algorithm can work in a physical stuff. Of course, there is a problem that mass has to be conserved. So as soon as the cards are replicated, the total mass has to be preserved, which is the normalization in some way. Total mass has to be preserved, so that means that the dimension of each card is getting a bit smaller. Okay. Every time you do an iteration, these cards are replicated, not exactly double, because otherwise the scaling would have been different. But let's say augmented in some way. Okay. And so if we find it's enough to have one other iteration, because we know this Grover algorithm is going like the square root. And so after about 17 minutes, I can find my book. Okay. So this is my PhD student, this is the book. Okay, thank you very much. So, see you tomorrow. If you have any question, I am available here. Open question, or if you think it's useful for everyone, we can do now, everybody we can do. Like now, yeah. That's growing out on working. Well, whatever you have interference, the piece is very difficult. Can you imagine you have to apply this algorithm one at a time? So after accumulation. So all the things that are based on interference are not really working well right now. So you will see tomorrow after the like variation of mathematical solver. I don't know if someone else has seen something like that. Variation of mathematical solver. Okay, but no one in this conference. So you will see that there are algorithms like variation of mathematical solver which are more robust against the norm. And these are the algorithms that are explored so far. That's the practice.
Okay. So, not a question, see you tomorrow.
Yeah, lecture 3. And then I think we have to do the PDF also the other one. So I tried to download this .1. I don't know, I have to download the Microsoft.
Okay, so I'm saving this one as a PDF.
Sorry?
I'm saving this one as a PDF.
Yeah, great. Direct from PDF. Yeah.
So I will convert the other ones to PDF and send it.
Yes, the.
Send it to my hand.
Oh, okay.
Maybe that was a mistake. I didn't send it to them.
Ah, yes, that's.
So that's sent to you, but I forgot that I had your email, my. But I will do it. Once I have the material for today.
See you on Thursday. Okay. I'll be glad to see you.
It was better to give a physical meaning of what I did.
Why did it need to do that?
I mean, the algorithm is doing many iterations of the different chips. One is to design.
Let's
And the other is amplifying what
I'm saving it. Oh, so that's the application.
So now the application, I can see. So that at the end, when I open when I all I will have all the one that I maybe I
Yeah, they did. Yeah, this morning. We started saying they do some of our stuff. This you need some like this morning we were explaining the whole pattern and things. That's one map. Such a large quantum express when I mean they are class.
Like it's in your case, I think so too. Yeah, I mean, there's no, but the perfect. The way you can drive the train.
I might have to introduce stuff with the cast.
Something to be like the classical. For which constraint we have? I don't know. We have to.
I was.
Yeah.
Put them to this one that you considering. But it also exists to make a search. Practice different algorithms.
So we need to just are you optimizing kind of distance? But everything, so you don't want to. I don't remember your problem.
Oh.
So you have two cigarettes.
Let's say I have four. Okay,
let's say you have 4 signals.
let's do two. Let's do two. So they're different, and I know where the differences are.
Yeah.
Actually, I don't. But I'm trying to figure out, so the current algorithm is how it works, the test for
So you have like relation, insertion,
yeah,
cutting, moving, flipping,
doubling, sometimes repeating. So but it assumes a consistent rate of these changes. So that is the main constituent of the will be.
Did you look in the literature?
Usually, I did, and they're saying for this specific one.
So did anyone want that? Because very often,
My word is.
say that, oh, basically all my ideas was this.
It's in there.
Sometimes you realize that this is not fun. It's fun because, okay, you did maybe one more step, you did something like that, it's not completely new, you have to try it, and okay, it's something that you extend and improve, not advance.
Yeah, it's already been done. Also, the other algorithms don't leverage, rather, they don't have the same constraint.
Okay.
Yes, yes.
There is something.
There is something, so it's just the one that's not there, but the other two not so much. And I think the other one is. Yeah, so I'm not.
So it's possible, someone has everything similar, you have to.
Yeah, it's sort of, they've done change it from that. But for the other two, really different, so for the other two, the same. The mind-open solution.
I don't know much about
Which is the energy of.
It's so curious about email.
yeah, I can write that. You are now.
But then you also have to.
Oh, we know you.
Yeah, yes.
Somebody does it.
I was very interested in the second examples for so that the Hadamard definition I was kind of curious. Well, I think it's probably a bit ahead of what we've done so far, but I can't across the key term, the social
Yeah, it's feature. But the feature is just you can implement the feature as a bit function. So the feature is the function. I don't know, you can imagine to have more functions, more features.
Yeah, let's say I have a typical data.
Oh, we have to go.
Just 1 second. Do you walk back or do you?
I don't know, I think we will find a way to do that.
Yeah, because I probably will walk back, I think, so.
I can walk back. I can come with you. I can come with you.
But I didn't want to interrupt it, no, let's
What is the supper?
where, I think there is a supper prepare, I mean, it's a takeaway supper, I think. I mean, what patients just asked you about, right, which choice you have.